nuclear, uranium in particular. Some grams of uranium have a high density in terms of energy. Okay. So it is the first part. Why there is no such solar everywhere? It's because there is other resources that are more dense, and so if you explode them for industrial purpose, it's more efficient in terms of business and economy, and but much more impacting for the environment. Then, from this resource, we need what? We need heat, we need electricity, and then we need, when we have produced this energy, we need to distribute, to transform, to distribute, and to store, and to restitute. Okay, that's so here also an issue for solar energy is to be able to convert. Some conversion are quite energivore, energy consuming in terms of efficiency, and for sure you have to think about storage to deal with the intermittency, night and day, and winter and summer, and where it's cloudy and sunny. Okay. Whereas for the other, you can produce constantly, and the storage is not an issue. Then what you need as a final energy, you need it, cool, electricity, and mechanical. And so what is important is that the characteristic time could fit. Whereas, for example, for solar energy, if we want to produce some hydrogen that then will be consumed, the time constant of both producing and consumption are different. For example, if I have a PV central to produce hydrogen with electrolysis, it will spend 6 hours in one day, in a fully sunny day, to produce amount of hydrogen. And whereas when I want to use it, for example, with a fuel cell to produce electricity, it will be consumed in maybe 3 hours. Okay, so sometimes it is longer to produce a resource than to consume. Very often it is the case for everything. Also, it's longer to produce than to consume. Okay, so it's also has to be taken into consideration. And also what is also important to consider is the scale. Which scale we are considering, massive or small quantities, and reversibility and duality. So it is this context that make also all the issue about the development of solar energy, and of course that we have to try to find solution. But it is not so simple as my first slide to say, yes, there is plenty of sun everywhere, so we should develop that. We have to take in consideration that the density has to be improved, that the time dynamic between production and consumption is different, so that there is also variability and intermittency to deal with, and at what scale we are considering. The advantage of the sun is that we can start from the small scale, local, your house, or solar application, just the domestic heat water for small installation, to big scale. Big scale, it could be a big central, or it's also big integration, massive integration at the scale of a territory, and especially urban territory. So we try to find solutions that will consume less and allow to produce integrated energy. So when I'm starting from the PV, we found some PV central, and especially in a big desert and in area where you can't do anything. Now in Europe it is very controlled. You have the right to develop a big PV central in place where you can't do anything else. That means if you can make, it is a field where you can make agriculture, you can't put PV like this, okay? Or you have to find solutions that PV will protect, will be helpful for the agriculture. For example, it could be a greenhouse with PV, so what we call agriculture PV, agri-PV, okay? But a PV central like this on a field where you can have animals, cattle, agriculture is forbidden. Also, where you can construct house or buildings, it's forbidden, okay? So now, at the time, we find some developments on floating PV, because on lake, we say, okay, we can do, it's okay, we can maybe try to put some floating PV. So there are many developments on this area. Also, in place where it was previously, I don't know how you can say, the rubbish, waste deposit. Okay, so in this field, it is very polluted. You can't imagine to build building because it's too much polluted. You can't also imagine to make agriculture. So for this area, it's allowed to develop some PV integration. Other place where we can't do nothing else, that could be big installation in your point of view. It is a big car park. Car park in cities. When you have a big shopping center, sometimes you have a big car park, and there is now obligation to put shading protection for the car. So that umbrella, PV umbrella. So it could be big surface. Okay, but for other ground where you can do something else, it's forbidden. So it's pushing also to integrate PV, and we will see different way to integrate that. And it has a sense because you can produce locally for a local need. So it's very interesting. So there is still innovation in the way to integrate it as a full components of building, and to use it also for other things like a window, like shading for the sun, like roof part, like tiles. Is what I will show you. If we massively integrate, depending of the country, of course, depending of the source, the sun, we can estimate that we can produce and answer 15 to 60% of the needs at the city scale. So it's interesting, including mobility plus the building. So now there is also more and more coupling between integration in building and try to answer to building needs, but also coupling with mobility and especially electrical vehicle. Okay, so that electrical vehicle that could be considered as a way to store energy when you don't need it, because it's a battery, and if you plug to your building, you can use it. So there is what is considered to be integrated to building. There was a big debate in the beginning of the 2000 years about what is integrated to building. And there was a big push to consider that only was PV is integrated to building if he replace a building envelope or a building element. Okay, so if he becomes a tiles, for example, like this, like you have Sanyo building in Japan, which is fully full of PV, well integrated, we can say. Whereas on the right side, it was not really considered to be integrated because it's just put on the roof as an over imposition. Okay, so there is many categories that is considered to be integrated or not. It is one, so on top of existing structure, that not provide a closed covered function. Okay, so you can find all the configuration, juxtaposition the roof, just on a flat roof, on a facade or shading. The C2 is integration taking part in closed and covered function. So it's a PV, but it is a full, also a completely entire building components. Okay, so tiles, windows, double facade that have a use for light. At the beginning of the 2000, it was only the integration in a roof south with a good inclination was also supported by subsidies. Okay, it was impossible to think about integration in facade in east, in west, but now it has changed. And here, for our latitude, the best inclination, if you want to maximize the production of electricity, is 35 degrees in France. Okay. But I don't like if you want to produce the maximum. Now I prefer if you want to produce in order to try to find a solution for your needs. It's better. So now we can play with also the other facade, the other orientation. So if I consider on my house that I am at 35 degrees, it is a reference to produce the maximum in France, so it is 100%. If I put on a facade, I will lose around 30%. Okay, so you see 70%. But the potential of facade is much higher. If you are not in a house, but in a tower, it's much higher. If you are southeast facade, it is a little bit less, but it's not so bad. You are losing 5% more, but you are around 65%. If you are on the roof east, you still have 80%, and west you have also 80%. Okay, so it gives an interesting idea of if we have different orientation, what we can expect compared to the best optimized full production in your place. I like this kind of diagram that give a quick idea regarding the place where you are to try to find the best integration, but then after to see the impact if you change this orientation. So it could be translated in what we call correction factor for orientation and inclination. And it's easy to identify if you are fully horizontal at east, southeast, and so on. Of course, for the horizontal, whatever the orientation, there is no impact. Okay, you are losing compared to the best inclination south and so on. But this is a way also to have an idea regarding your building environment to see the solar potential finally, depending of each facade. So at that time, we try to model that at a city scale with kind of scan, geometric description of the city, and put on each building envelope this kind of factor. to have a look and to have an overview of the solar potential at the city scale. Okay. Also including the mask that we have seen yesterday. The mask is very important, so it could lose a lot in terms of performance. It generates, if it is local mask, so just a small shadow on your PV installation can generate mismatch and then difference of operating. Difference of operating is not very good in terms of performance, but also for all the electronic components. So it's very important to clearly estimate this mask. So we have seen how to do it yesterday, and to plot on our evaluation of the rays of the sun in the sky or obstacle, so that if they are far or if they are close, is the same way to plot it. All the tools, of course, are dealing with that. Architectural integration also is a constraint, because if we want to push for massive integration of PV, we have to show architects that everything is possible, because one of the main barriers is architecture, and so to show them that there is various color that is possible, that you could integrate also in historical building, and in mimicking some wood, some stone. You have also natural light, okay? So they don't want, of course, to put some opaque PV panels if they want to play with the light, and there is heating requirements, cooling requirements that have to be done. So, of course, you can't recover all the building of PV, or except if it is semi-transparent. And so you have to take care of visual, thermal, and acoustical aspect. So regarding a very recent PhD that has been defended in my lab, so it is a PhD of Benjamin Riedel, we played with aesthetical. So we have developed a standard PV modules that you can see here. It is made by the CEA at INES. And with that, we were playing with the different color and the originality that we were printing on these PV panels. And so we were mastering each point of the ink, okay? So we were playing with the space between each point and with the color, and with the color red, blue, and green, to give the different aspects and to have a far away aspect, okay? When we are close, you see that it is point. When we are far, it looks like fully white, fully blue, and so on. So, of course, the issue for this was to limit the loss of efficiency, okay, and so to optimize the printing with the loss of the color and the loss of efficiency. At the end, we were able to print like if it was a stone, gray, like a stone, or wood aspect, or terracotta also. And with this kind of manufacture, so it's printed afterwards. You print with ceramic and then you hit, and it's not move. It's perpetual printing. You can also imagine to make some motif on the facade if you want to draw a big head with PV panels and so on. There was interesting results, especially regarding the white. The white is cooler than the classical PV. And but and there was also more diffusion after the layer of the printing, and so finally the performance was not so bad. But we were losing some performance depending of the way to print, of the color. As you see, we can reach 45% of loss due to this. But it was interesting to show that everything was also possible afterwards on a real PV panels for integration in some, for example, historical building, cultural heritage building, where you have to develop specific aesthetical aspects. So it was
How this dye is injected there? How this ink dye is injected?
It's a real printer. So it was with manufacturer printer. You were a big printer, like where you are making the map of some buildings. So you put the ink was ceramic ink. So he was mastering where you put each dot to print. So and then heating, and then fix it on the. It was very, very interesting. So other kind of integration. So when you have a flat rooftop, this kind of integration is not so aesthetical, but it is at the level of the roof. And what is interesting is that it could be ventilated on both faces, whereas for other kind of integration is delicate, as I mentioned. When it is on the building, there's a face which is delicate to ventilate. We will see what we can do, but here it's ventilated like a normal PV central finally on each side. So the performance are more interesting, and also the access is more also easy for the maintenance that it is if it is fully integrated in the roof, for example. Okay, the problem that you can have, it is that you can also make some hole in existing étanchéité, waterproof layer. So there was a lot at the beginning, a lot of damage like this, because people were just making hole, fix the PV, and there was many leak after, and so problem of insurance and so on and so on. But now it's much more mastering. Here some PV, fully PV integrated as aesthetical. So it is a full component of building. It replaces the tiles. We have developed with Imeris company also integration of PV on the tiles. It was interesting results, because there was inertia due to the tiles, to the terracotta, and so during the day, when the temperature in summer was increasing, these PV modules were more inertial, and so there was a delay between the peak in the afternoon. For example, the hottest time in the afternoon was 4 o'clock in the afternoon, whereas the hottest temperature of the PV panels was 5 o'clock in the afternoon, almost, when the temperature outside was decreasing. So it was interesting to add thermal mass. It's like if you had finally a kind of phase change material at the backside. Of course, there's one thing that has been corrected after, that we can see on the picture, and it's not good. What do you see in the picture? Shadow, self-shadow. So then after we put the sails on also on the inclined part, and the tiles were flat. Okay, but it was the first attempt. So they're self-shadow, so it's not good. Okay, so other way to integrate, you get rid of the tiles and, sorry, there's some French, but you can guess that it is to put some waterproof layer at the back side. Okay, integrated as a glazing. So I showed you yesterday my green and pink double facade. So we were working on the company that have then used it to to build the Cité de la Voile of Eric Tabarly. So it's the same principle of the facade that I showed you yesterday, playing with the color and playing with the density of the cell. Okay, so the company was Total Energy at the time. Now it became Total Energies, and the architect was Jacques Ferrier. So it was a result of what we had developed together to show that everything was possible in terms of density, color, and so it was happy. There is also another integration like on a railway station, you can see. Okay, you can have the same kind of thing in a facade. So you can just plug over the facade, it is superimposition. Or you can have also some structures that are independent of the existing building. On the facade that I showed you yesterday, they were self-porting. So they were independent of the house. You see, there was a house and the facade. The structure that has been built in aluminium was autonomous in terms of mechanical strength. Because it is important if you want to add an existing building. Usually, an existing building, the structure has not been designed to accept a new weight, and a PV module could be very heavy because it is glass. Okay. Also, integration as a sunshade. So this is considered to be a full component of the building. Because it helps to protect from the sun during summertime. Here also you see an existing building in the south of France. It was a historical building, and the architects had a double skin facade, PV ventilated facade. So it was helping. I will show you the operating configuration. For winter to recover heat in the air gap, okay, and for summer to use it as a natural ventilation system connected to the ground, because under this building there is a cave and it's cool air. So during summer there is chimney effect, and so the cool air is going inside the building. Okay, so the main guide that you want to develop BIPV is to be cautious of the operating temperature, as we insist, and to find solution in order to avoid too much increase of temperature of the PV panels because of the dependency of this conversion. Is also to try to highlight and to enhance and to recover a part of solar energy which is not used for electrical conversion. So how to use part which is thermal part, it could be interesting. So I show already you the two way. That more active way is to master the fluid circulation, okay, a calorific fluid. That could be water, oil, or water, oil, or air, or a passive way, where you just try to find solution that passively will allow to decrease the temperature of the components. And the best is natural ventilation. So to try to find or siphon phenomena to find natural circulation. The components so that we have developed, I show you the double skin facade on the greenhouse. We have developed for existing office building. Also facade, you can see that it is not completely flat because the orientation was not optimized. It was not a south facade, it was a southeast facade. So we developed components that allow to give to the PV panels a good orientation. Of course, in the other side, it allows the light to cross. You can't put PV panels on both sides because it will not be optimized and it will create a self-shadow effect. Also at some.
Southeast orientation. Why southeast orientation?
Because it was an existing building. We want to demonstrate that one of constraints of the existing building is that the structure are not really designed to accept a new weight, and also that the orientation have been chosen long time ago, and you can't turn the. So we want to show that even the facade was not fully south. There is some adaptation, nice aesthetical adaptation that could allow to optimize the orientation of the PV. We went also on solar steel, so it was to integrate on steel for application in industrial building or stadium, big stadium near Lyon that have these PV panels. We've also Umicore, which is zinc. You know in English comment on dit zinc. It's not iron, it's zinc. All the roofs in Paris are in zinc, and they wanted to develop such a kind of component for putting on a roof, but it was forbidden by the city of Paris by aesthetical aspect, heritage aspect, and at the back side we were using ventilation of air and recover air for the building need. So for the prototype that we are developing, we are not manufacturing the cells, but we are able, especially in collaboration at INES with the CEA, to manufacture PV module. PV cells is delicate. The CEA is developing some PV cells, but we have no skills on this scale, except some maybe some thin film that could bring something in like photonics properties, but we don't at that time work on this scale. We are working more than on the design of the PV modules and adaptation to the final configuration. So I show you this, but I didn't focus. No, on this one I will focus later. So the way we have designed the heat exchanger and the coupling with the PV cells. So before going to more active operating condition, I will go on the ventilation and what we have done on this. So first, now we are developing building envelope, so that include ventilation, natural or controlled ventilation, that are active in the way that they are producing some energy, and multifunctional that they could also evolve depending of the building needs and of the climate. So we don't work on just passive neutral components. Okay, so we want that these components provide combined function as insulation, preheating or pre-cooling, heat energy storage, electricity generation. Okay. So is the main configuration that we have studied. So Pareto dynamic wall. So with ventilation, with an air gap which is ventilated. Also, we have worked with Pareto dynamic windows. So it's specific windows that allow to an air inlet by specific pass. You can see there is free glass. The inlet of air is here, going down, turning and going inside. This kind of windows is interesting to recover a part of it during winter time, because winter time when it's cold outside, the more deperditive component is the window, and thanks to this air pass, the heat which is going from inside to outside is partially recovered. So and it is interesting when you have only one flux mechanical ventilation. So the principle is during winter time you will the more simple is to use it as a double glass finally. So there is an air gap, it is closed, there is watertight, it used as insulation. The other thing is to have a more active mode, that to use this air gap as a way to preheat the air. So you can have opaque PV wall, then the building envelope, and you ventilate this air gap to recover a part of it. That could be coupled to the heat exchanger for winter time or to heat pump, because you increase a bit the inlet air. You can use it during summertime as a free ventilation system. So if you're on the south facade, you close the bottom, you open the top, and you allow the air to go from inside the building to outside the building. And in principle, the fresh air which is coming from the north is cooler, and it will allow to cool the building because it's cooler, and also by convection. You can also combine, it was a historical building that has been refurbished that I showed to you, with a pass of air going underground, where the air is more cool. So it could be Canadian wheel, or so finally you are decreasing the temperature of air because there is a pass underground before going in the envelope or in the building. But so it's to use it as a natural ventilation system, playing with the chimney effect due to this. This has been developed in a very hot country like Iran. I'm sure in India also solar chimney or wind catcher to enhance natural ventilation when there was no mechanical possibility. So we work a lot on this chimney that allow to cool the building during the summer and to bring some heat during winter. I think you know all this. We didn't work really on this. It is a solar wall. So it is a perforated steel skin. Have you seen that? So the first skin is a micro-perforated steel skin, black, okay? And so the air is going inside the air gap all along the facade. And so is heated, and this air is then injected in the building, okay? Of course, you have to add some filter. So it's solar wall that has been developed by the company Solar Wall, which is a Canadian company. So it's like an uncovered solar thermal collector, okay? Uncovered solar flat plate collector, but the originality is that the absorber is micro-perforated, okay? So the inlet of the air is all along the facade. So it's worked well for the preheating, and it is the reason why it has been developed by Canadian, because some few degrees during winter when it is very, very cold, it's important. But the function in terms of refresh potential has not really been studied. There was some attempt about such a collector to use it at a reverse way during the night in summertime, and to enhance the radiation exchange with the volt, Celeste volt. Okay, so if the building is hot, you blow the air and through this double skin envelope, and you can this black body can emit radiation with the Celeste volt and cool down the air. But it has not been very well studied yet. For this performance, we can win between 5 or 25 degrees, depending, of course, of the sun and of the temperature outside. So it's interesting. This is on a building at in the University of Lyon, where I was previously. So it is the aspect of a real solar wall. It has been installed for practical lecture for the student, and also, see at the backside, it's a big industrial building where there are all the practical work of the students. There is a different energy system and so on, and so it was used during winter time to heat this building. So the target of such components is more tertiary building, office building, commercial, agriculture also could be interesting if you want to maintain a certain level of temperature in a big space, and it's quite robust. So this is the configuration that has been here. It was on 2 floors, and there was it was directly coupled to the HVAC system. So then you can upgrade if it's not enough by a heat pump before blowing in the building. Other system, it is a trombe wall, so there is many development about this. At the beginning, the idea was quite simple. Trombe was living in the Pyrenees, so where there is a big furnace I show you. In the same area, he was working on solar energy. He has a big house made with big stone, so very huge thermal mass. But it was very hard to heat this house because of the thermal mass, and it is very cold area during winter time. And so he tried to put a glass in front of all the wall. And he has seen, yes, that greenhouse effect was very interesting. The stone was very hot. So he said, oh, I will make some hole in my wall and put this glass, and he use it to preheat, to heat the house, and at the back and the stone of the wall of his house were finally storing the heat during the day and release the heat inside the building during the night. Because at that time, such a house, it's a typical house, it's only stone. There is no insulation. So finally, during the day, the sun was impacting the stone. Thanks to the greenhouse, the temperature was increasing. And the time that the heat was going inside the house, it was the night. So it was so since that time, there was many development of the principle. You can put phase change materials at the backside to store the energy instead of big. There was some tunnels, some barrack of water instead of stone, and many. It's a very interesting principle and simple principle that could be adapted on each a lot of configuration. So the principle of the operating is that you have all, of course, on your in your house. So it is your the main building envelope. Okay, you put a glass. Okay, and you make it possible to play with the opening here. Okay, so the classical one is the windows which is not moving, a glass which is not moving, and so during the day he was opening, so there was a chimney effect and circulation, a free circulation. Usually the cool air is down, so going inside, warming and going inside by thermosiphon effect. But then, so it is the main trombe wall, originally a trombe wall. There is protection, of course, for summer, because for summer, if you don't protect, or at least you have to erase the glass because it will be too hot. Okay, so you have to add shading protection for summer. So this is the house. So you see how it looks like. Just had some windows on the house. The optimum, and you see the shading also. The shading at the top for the summertime. So when the sun is very high in the sky. So in terms of characteristics, the optimum orientation is south. It has to be at the backside EV materials or phase change materials. The air gap is around 3 to 6 centimeters, and the inner wall was at that time 30 centimeters of stone. Double glazing is better, that you lose less some energy. The performance is quite good and could cover for such a facade. You see, the facade is important compared to the house. 70 to 85% of the heating need without mechanical assistance. It's fully natural, and the wall can reach 65 degrees. So it was the stone was quite high. The evolution of this, so it's a zigzag solar wall that you can find with a different section and different orientation. So you can see southwest, southwest, and different composition if you want to store or not. So there was one southeast glass section to promote heat and light. So it's a mix with what I showed to you. In one side you have the PV, in the other side you have the glass, in order to allow light to come and to optimize the sun collect and sun use in the south. So interesting also study. This also, instead of stone, there is some container of water. You can see different picture in the 80s. They try to integrate inside also the house a container of water, more or less integrated in the house like a column, to add some thermal inertia. You have collectors with PCM, so I mentioned. Instead of big stone or heavy materials, you can add phase change materials combined with semi-transparent PV. So, for example, here this system that has been really implemented, they were using hydrated salt, and so of course the key element is to choose the phase change temperature of these materials in order to optimize the operating configuration. At that time it was for winter, so to recover as much as possible heat. So after you can find with combination of thermocirculation, control inside the building envelope, integration of ventilation inside. Okay. So one of the key elements of such a facade, to recover part of heat during winter, there is many configuration with heavy materials, and for sure it will be mechanically ventilated if you want to increase the efficiency. Like this you control the air velocity. When you want to use it during summertime, it's more delicate, because you want to use this kind of element as a chimney, a natural chimney, natural ventilation system. And the natural ventilation system is very dependent of external and internal conditions. If you have wind on a building, you have some facades that are in surpressure, some other facades that are under pressure. You can also have wind that is going in your facade and go at the top of the facade and go down, so that you want to avoid that. You want your facade to be a chimney. So wind and natural ventilation is complicated, so you have to know very well your environment, where and what are the dominant wind. And also you have the thermal aspects, because the chimney effect, you have only two ways to naturally ventilate it, is to use difference of pressure, so to use the wind, which is very strong, and to use the difference of temperature with height, so the difference of density. It's the only two natural engine of the ventilation, is difference of pressure or difference of temperature. And if there is a fight between difference of pressure and difference of temperature, it is the wind that will win. Okay, the wind is much stronger than difference of temperature and air movement induced by difference of density. So it's complex. It's complex to design, and also to find solution in order to be sure that there is a good enhancement and heat transfer in such configuration. So we implement that, I told you, for both, because we wanted during summertime that the air is coming from the bottom and be extracted from the top. Okay, so of course we have to be sure that, for example, especially here, that there is no local dominant wind that is in the other direction, because all that you are expecting by natural ventilation due to chimney effect could be completely neutralized by dominant wind that will come and blow inside. Okay, so it was not the case, hopefully, and so we have made some experimentation to look at. So what we saw that, of course, the density of the sail have a big impact, because it's allowed to hit the first facade or to hit the second facade. So you have finally a kind of ventilated air channel with double flux, with a double wall that are partially heated in one and partially heated in the other. And we find it was good to have a asymmetrical heating of the first facade and the second one. That we find that it was allowing to generate turbulence, and so to improve heat transfer in the air gap. We have also done that for the natural ventilation of this facade, so in this existing building, which is an office building of one of the partners.
But anyway, these channels are like fixed. No air can enter.
What?
This channel, nasal ventilation, only some selected holes will be there through which air will be circulating.
No, at the beginning we didn't select the density in order to have the best ventilation. We just select the density of the cell in order for summertime to protect, to identify where the more irradiate zone to protect the house. But then after, yes, the air is during summertime could come at the bottom and could be extracted here. And we find that thanks to the non-symmetry between the two walls, the glass wall and the wall of the house, there was some part more heated on the wall envelope of the house, more heated on the glass wall, and it was good in terms of development of turbulence inside. So it's a facade that we hadn't instrumented, and we try.
Is there any calculations like when you say this non-homogeneity of the cells, and then we need micro inverters?
Yes,
Micro inverters.
it was micro inverters.
So every module you need micro inverter.
Yes, for sure. Yes, because the density is different. So for all these installations, there was one micro inverter per module.
Then it should be very costly.
Yes, but it was research. So, and the partner, one partner was a PV manufacturer. So it was interesting to see. It was quite new at that time, the microinverter. So it was interesting to test that for itself. One was an architect. He was interesting to show that we can play with the color and the density. One was Technal. Technal, so is an aluminium manufacturer. So it was interesting to develop. What I told is that we wanted. This is experimental house of EDF. What we wanted to show also that we can integrate PV like this, which is quite enormous, without new constraint on the house. So it's self-mechanical independent. We didn't have weight on the house. So the manufacturer of aluminium frame was interesting to develop such a system to show that it was mechanically independent, stable. So every partner want to test new things, so they didn't look at the cost. It was very lucky. Yes, yes, it was.
Has their own no,
Yes,
agenda.
their own objective in the whole project. Yes, it was interesting. So here it is some results because we have made some experiments on the facade, for example. So it is result presented on the shape of a carpet plot. That means that for every day we were plotting hour per hour the velocity, for example, the irradiation. Okay, so we made a lot of carpet plot like this. So each ray is 1 day with many different many different data. Okay, like this you can see where is the winter easily. Here it is the flux which is received at different level of the facade. So you can see where is the winter, where is the summer, and there is some problem that we have identified. The facade was in Toulouse, not where we are. So here, for example, interseasonal problem. So it's between winter and summer. There was so we investigate such a thing. So we try to model also the double skin and also to evaluate the temperature. So this is the temperature of the PV facade and try to recover. So finally we find quite satisfactory model that could give the evaluation of the temperature of such components. So it was a mix between physical and data. At the time we didn't we were not speaking about data deep learning, but it was yes, extracted from the same kind of approach. We were also it was also easy to identify the problem. One of the problems that after we implemented the facade, they put some trees, small trees, and we were not aware about that. But when we were analyzing the data, it's on the bottom of the facade seems to have a problem. We don't know why. Maybe it is a sensor which is not good, and we didn't understand. There was a change in the behavior at the bottom of the facade. And finally, for a meeting, we went in place and we saw that at the bottom of the facade there was a tree that has leaf, and there was every day for a few hours shadow at the bottom of the facade. And we were trying to model that. We don't know why it's like this at the bottom of the facade. So this kind of diagram is very easy to identify if there is some problem or not. Okay, so I will not go deeply, but of course we wanted to be as closest numerically and experimental data. It is so we have developed quite also simple model because first was fluid dynamics model, simple model that could allow to manage this double facade and the air ventilation. So it's a simple analogy zonal approach, and we were considering 3 main levels in the facade. It was a PhD also. If you are interested, it's in English because it was one of my PhD that was work on this modelization. Of course, when it was mechanically ventilated, the results were very good, and when it was natural ventilation, the results were very delicate, especially when there is some wind. It's difficult to take in consideration the impact of the wind. So it has been developed in Terenzis and give so with natural ventilation, it is this kind of equation so that provide that has been developed by Brinkworth that provide the evaluation of the mass flow rate m, air mass flow rate. It was quite good in stable condition. As soon as there was wind, even a small velocity, it was very complicated. But in some stable conditions, so sunny, without wind, it was quite good. Okay, and also when the solar radiation was low, it's delicate. When you have a low solar radiation, it's delicate to have an exact. It's better when you have big solar radiation. The phenomena are very strong, so you are more accurate in your prediction. When the value are small, it's delicate, but it was good at the end. So here you can see with evaluation when there is wind, there is different results. It was a problem. Okay. Other kind, so that we don't develop that other kind of PV, BIPV hybrid integrated. So it's a mix with the finally the solar wall that I showed you previously. You can see the inlet in between the PV modules and PV facade. So it's also interesting. They were playing with the protuberance in order to generate and increase, to generate turbulence and increase its transfer. It was an interesting study. So you see here the products that could be considered to be well integrated, especially in the right side. And they were playing also about the distribution. Okay, so for the efficiency of hybrid PVT, I will not spend time because we have seen yesterday the thermal and exergy efficiency. We can also, if it is coupled to a heat pump, try to combine the performance coefficient and the heat pump also coefficient. So this is some attempt to combine both. So is this
is fluid is air, right?
Yes.
Fluid is air.
Yes, with air. I'm still with air at that time. Yes. So interesting. Okay. Yes, of course, for ventilated facade, the mass flow rate is important for the efficiency. Okay, like we saw yesterday, the flow rate of the water is very important for efficiency of PV cell, but less for the thermal efficiency. So depending of the mass flow rate, of course, the more the ventilation is high, the more the efficiency of electrical function is high, but the efficiency of thermal is low because you can't increase too much the temperature on the air. Another ventilated facade roof that we have developed in real application, it is on the framework of Horizon PV, so it is an industrial wine storehouse. So it was interesting, not because of the wine, but about the characteristic of the building. We want to develop an installation that could produce massively electricity. So because to use an big industrial structure roof, it's interesting, and also try to answer to a part of the needs of the building. What were the needs of the building? So the building was mainly composed of tank of wine. Okay, so very heavy. The building is has a big thermal mass. Okay. It is on the south of France, so during summer they need to cool. So the PV was using to use classical cooling system. Okay, but during winter, the temperature has to be between 14 to 18 degrees inside. And so we said 14 to 18 degrees, it should be possible to reach that without heating system, but just recovering the heat under the PV panels. Okay, and so the development was, so the constraint was the roof slope was not important, only 1%. So we decided to put on both sides of the roof. Okay. The tank side, so inside is very important, so very inert. So not all the roof has been designed to recover the heat. Okay, so we've made some computation in order to evaluate the size, the surface of the roof that we need to be hybrid, photovoltaic thermal. Okay, so I don't know where it is. So there was, finally it was 50% PV, so only PV, not ventilated, and 50% of PVT. Okay, of course we designed the also inverter. There was 3 inverter depending of the specificity of the installation. 3 inverter for PVT and 3 inverter for PV, so 6 at the top. The thing that we have developed is an integration of the PV module, so through this aluminum frame. So the PV module were fixed on this aluminum frame, so there was air inlet and going through the PV. So the ventilation was between PV and aluminum frame. Okay, and so it was tight, airtight. So when we put the PV panels, there was air tightness around the PV panel. So it was a ventilated channel. In one side it was PV panels, and in the other side it was aluminum. Okay. So of course you need to develop also the ventilation tubes. So here you can see the ventilation system. So to recover at each row the preheated air. Okay. Then this air was directly blown inside the building during winter time. Okay. What to do with that during summertime? So the idea was to continue to use this heat during summertime, and the needs they have during summertime, so to cool because they have to maintain the wine at a specific temperature, but also to clean. So the big tank during summertime they were putting the wine in bottle, so they empty the tank, the big tank, and so they need hot water to clean after when it is free of wine. So we had on this design a heat exchanger, which is not so common, between air and water. Usually it is the other way. You use hot water and exchange on the air. Here it was to exchange, use the air and exchange on the water. So it's not so good in terms of heat capacity of air, but the quantity of air was massive. Okay. And thanks to that, to produce hot water, during summertime that could be used for cleaning. Okay, so finally this installation was also designed to work and operate the same way summer and winter. But summer we were not using the hot air for heating the building, but for heating some water.
Is this PCM or?
No, the tank? No, it was a big tank of water. No, yes, because there are a lot of place in this building.
Insulated tank, yeah.
Yes.
What's the temperature there?
60, we were reaching 60 in the tank with only hot air.
And there they use PVT.
Yes, we were using this system of PVT winter and summer. But so winter, the collected hot air was directly injected in the building because it was enough to maintain the temperature between 14 and 80. Okay, preheat, but it was enough. And during summer, the hot air was oriented to a heat exchanger with water, which is not so common to use air to heat the water. But regarding the surface and the flow rate was important. It was enough to heat the water at 60 degrees. That was enough also for them to clean the tank.
But when this heat exchange is taking place from air to water,
yes,
we are losing a lot of, because this side is air side heat transfer coefficient is very
yeah, yes, that's what I was telling, that it's not so good because air capacity is not good compared to water, but the quantity of hot air was important and was enough for producing the water. Yes, we never saw heat exchanger like this. But the idea was for them to be autonomous in energy and no need of energy. So even if it was not so efficient, at least we could use the system also for summertime to heat this.
clean the bottles.
Yes, to clean the tank. I don't know what time is it. I have time or?
30 minutes.
30 minutes. I have 30 minutes again? Okay, good. Okay, so we have developed also a model, the same approach. So this is a cut in the channel of the hybrid PVT. So here you can see the roof. There was insulated roof. Okay, there was iron, and as it is an industrial building, so insulation. Then there was the air gap. There was aluminium frame, and the air was going inside here between PV and aluminium frame. Okay, so the airflow was here. If I'm coming back, you see there is an air gap down here because we couldn't be fully on the roof. So it's only fixed here on the side. There's an air gap which is not used between insulation and the wall, and the air is going between aluminum frame and PV modules. Okay, so insulation with air gap which is not used, and the hot air is circulating here. So it has been implemented on Terrandis also, and for each row and each zone coupled to the ondular and inverter and things like this to model the whole installation. So we found that there was around 10 degrees of difference. So to remind you, half of the roof is fully PV, not PVT, and half of the roof is PVT. Okay, So it was also possible to compare in the same condition the impact of the ventilation on the PV. And so we find that there was maximum 10 degrees of difference between PV and PVT. So better production of electricity. Sorry, it's in French. I have left some, but it's classical numerical and experimental comparison. It was interesting to compare with the PV, simple PV, in the same installation. So we found that it was not so bad. We were able to evaluate what was recovered. What was delicate in this area, it is in the south of France, and it is very windy, very, very windy. So when there was wind, it was also delicate at the beginning, to find the results. And you see, it's very, very windy. It's along the Rhone River, so the roof was fully ventilated, of course, because it's at the top of the building. So the impact was important. Okay. Well, this is classical results. So the flow rate at the heat exchanger, to give you an idea, was 2,500 cubic meter per hour, and we had a minimal temperature of 27 degrees. So when it was not a good day, because the grid natural fresh water is at 15 degrees. So the more pessimist day, we could only hit the water temperature at 27. But the optimist day, we could reach 60 degrees. Okay. Okay. So we made different parametric studies on this. One thing for such a ventilated envelope, which is important, is the fire. Okay. And especially when it is vertical envelope. Also we work on the way to find solution. For example, for the facade at Technal, the aluminium office, we find solution in order to avoid, if there is some fire, the development of the fire all along the building finally, because if you want to enhance the chimney effect for sun, if there is a fire, you will enhance the chimney effect for fire. Okay. We also design something that will, in terms of fire, could contribute to stop the fire or to cut the airflow. So this has some separator. We have tested some separators that could close between each floor. We were also thinking, but we didn't develop that some things that could open the double skin, so leave air crossing the PV facade. Okay, like this, if you leave air crossing the PV facade, it's neutralize the chimney effect. Okay, so we don't develop that, but it could be a solution. Or we tested also some springles, so springer. So you put also injection of particles of water, which was not so bad. So we tested two things: mechanical that close the chimney and sprinkle, to be sure that it could be also developed in a real building where there is inhabitant. But it is important when you are focusing on chimney effect to deal with that problem, to think about that problem when there is a fire. In terms of new development now, so what I showed to you until now, it is aesthetical innovation. It is ventilated facade that could have a function for winter, so heating need, a function for summer, for cooling needs, okay, natural ventilation. We try to develop things that now can evolve by themselves. So also that combined with properties that could also change. Okay, at the time it is the operating configuration that we are changing, but not the properties. Okay, so we try to develop new kind of components that have properties that can change. So this is not us, but it is some application. Here, if you can see that kind of, so it looks like air balloon. So, for example, this is a good insulation. When it's like this, it is a good insulation. If you, during summertime, you want to get rid of this big coating that keeps the heat inside, you can imagine to unflatted this balloon. And like this, there is no more insulation. Okay, so it is a principle of, finally, a facade that could have properties which is changing. Could be a very good insulation, and if you get rid of air, no more insulation. So we try to find something like this. So things that could allow sometimes to leave. So it is still my double facade or my double. So can leave all the solar energy crossing the double skin, or can become opaque in one. Could become opaque in one and collect the solar energy, or could become opaque in both and just hit the hair, or become opaque and inert.
It's earthquake. You got.
Sorry?
It's earthquake.
What?
Earthquake.
Yes. What was earthquake?
You experienced this?
Ah.
Just now there's an earthquake.
Ah, okay. I continue?
Yes.
So, or it could be non-uniform in one side, partially, fully. Okay, this is, it could be used naturally or mechanically, and so different configurations. So, with thermal and PV, we can imagine to do that. So changing the properties, optical properties, changing thermal mass insulation properties, changing transmission properties. So in order to be able to finally evolve, to have evolving components. Okay. So for this, we try to look at in the nature. In living organisms, what are the mechanisms that could be useful to implement in the facade? So Kita is well aware of this. So for example, and what we find interesting is two things, insect or plant. Because finally, if you look at this building, and if you look at the insect, they have a common point. What is the common point between this building and an insect? Is that the insect has exoskeleton, and the building has an exoskeleton. the insect, mechanical property of the insect is the envelope, like the building. And so how he managed to deal with all the thing, all the exchange with the environment through its envelope. Okay? And so through the envelope, so we call that cuticle, okay? He is breathing. The insect is breathing through his cuticle. He has some hole all over his cuticle, and he has no, how do you call the poumon? What is allow you to breathe?
Lung and heart.
Lung. He has no lung. It's just by natural ventilation. All around the insect envelope, there is different pressure. Okay, in a building, in this facade you will have maybe surpressure, and the other for sure you will have under pressure. Okay, this is the same for the insect. So all is managed by natural ventilation because of the difference of pressure all along his cuticle. He has no heart also. He has a different way to make the blood circulation. So finally, and it's the same for the plant. The plant interface, so the cuticle of leaf, are managing everything. They manage some water exchange. Of course, the insect also is managing the water because it will be fully dry when it's hot. So it's managing the water, it's breathing, and you have a lot of different particles that could be cross or can be filtered. You find also that in hot country, when you have a zoom on the leaf, you will find something like this, and it will induce turbulence when there is wind in order to cool down the leaf. Okay, in some other place you will have a kind of small water tank at the surface in order to manage water when there is matter, not water. So you have also a lot of different optical properties. In hot country, they have to protect against UV. Okay, so it's UV reflecting. It's a protection of the cuticle. The butterfly wing for insect has beautiful optical properties. It's incredible. As I mentioned to you, the anti-reflective coating on the PV cells is made like the wing of butterfly. It is powder, and what is changing in terms of color, it is just the weakness of the powder layer, okay? Because there is interference with wavelengths that give the color, but just is the same materials, but just playing with the wetness, it will interact with another wavelength and give another color, okay? But it's more complex than that for the butterfly. The optical properties are changing a lot with the direction of the radiation. You can have radiation coming perpendicular to the butterfly wing and have high emissivity, for example. And when you are 60 degrees, you have no more emissivity. And all the properties are changing like this with the angle. So we find that it is not for solar energy. It is to be protected in the nature, is to be protected. And so we find that it is to be protected from the birds. When he is flying, there is a double protection. He has a random flight. The butterfly is doing like this. And so this random fly, plus the fact that the wings are moving, the optical properties keep on changing, and the assumption is that sometimes the butterfly can be seen by the bird, sometimes not. Disappear, appear, disappear, appear, and with a random fly. So we think that it is for protection against attack of birds. But optical properties are incredible, and we don't use that for building. For example, we can imagine for winter, when the radiation is quite perpendicular to the facade, that it will absorb maximum, have a big absorption. For summer, when the incidence angle is bigger, it will reflect with the same materials. So this is kind of, so we try to. So the last thing that we have done, it's also in a PhD with Julie Raconton-Very, it was to work on the adaptive facade. So with PV, double B-phase PV. Here you have PV, okay, semi-transparent PV that can convert energy on the front face, but also energy on the back face. We call that B-phase PV. It is used on big PV central when you can have direct radiation, also reflection on the backside. Okay. So for this envelope, we wanted to develop a principle of adaptive facade. So here on the skin of this facade, we have developed this kind of B-lame components. So it's two materials that have different way to dilatation with temperature. So as they are together, but one, when it's hot, try to go in this direction and the other no, it will generate inflection like this. Okay. So we develop that on the fact that here we put a reflective coating. The principle, it was the first attempt, is that during summer, the sun is higher in the sky. So we'll cross the PV or not. And here at the back face, you have an inflection of this component because the temperature is higher. Okay, so when the temperature is higher, it will move, and so it will create a kind of mini concentrator. Okay, that will reflect the radiation that go through at the backside of the PV. During winter, it is cold, so this will not move. It will be stable, okay? So it will remain on the skin of the building. It's good because the rays of the sun is lower in the sky for latitude, and so it's more horizontal and go through the PV facade. That could be reflect or absorb the radiation for the building, because the building need also energy gain. Okay, so like this, it is more close to the building skin and can keep heat to transmit to the building and reflect a part also to the PV. So it is what we try to keep on developing, so to have adaptive facades that can have functionalities that can change by themselves and can be benefit for depending of the season to the building. So it's a kind of example that now we have a new PhD trying to go on this direction by also playing what I was telling you, photonics properties, so optical properties that could be also interesting depending of the angle of the radiation.
What is the material? The material what you use?
It is aluminium plus kind of polymer at the backside, a film polymer that is more rigid than aluminium. Aluminium want to move a lot with temperature, and it is
material having higher thermal conductivity. Material having higher thermal conductivity.
Yes. Just maybe to finish on this, making a zoom on the PVT that I presented to you here. It is about the absorber. It's the same mind as a bio-inspiration. The absorber we have developed is a frac-term absorber in aluminium. So you can see here the flow of the water. So it is made in aluminium, and so it is a kind of leaf. The advantage of such a grid of water is that the pressure loss is limited, and the temperature was quite uniform at the surface of the heat exchanger, because at the surface of a heat exchanger we put the PV cells. Okay, so it was just the innovation about that has been tested in a control bench at INES. So it was artificial light, artificial wind, to test this component in a control condition. So we found that the thermal was very good, thermal performance was very good. We were, I think we plot that, no. Compared to a classical solar thermal, it was quite comparable. We could reach temperature around 80 degrees. Electrical performance was also good. The main issue regarding this collector was to manage independently thermal and electricity, because if you want thermal, you are destroying the PV function, and if you want PV, you are not enhancing the thermal. So after we have developed a way to use it only few hours during the day for domestic hot water, and then after to prioritize the PV production. I have finished for this overview of innovative PVT, BIPVT, and I'm ready to answer some questions, if you have.
The presentation is quite impressive, and I know we have learned many things, new things.
We are playing a lot. No, it's interesting.
It's interesting. If you have any questions,
Sir, actually,
you can use that one.
it's okay. Right now you are working on
Yes, yes.
means you are so it's general question, like you are working on PVT with different working fluids,
Yes.
and you also has done research on water, air, and everything. In my case, I'm working on PVT with water, but means for better harnessing the solar PVT. So what you will recommend, like for PVT water or PVT air for in future?
PVT water, the main barrier is level of temperature that you can reach if you want to produce it. Because on on this experience here, clearly, the main we had at the end a very good PVT
Yes.
collector,
Mm.
covered, but it was too strong for the PV function. It was good for the thermal function, but too strong for the PV function. So uncovered seems to be the best solution. But how to be able to reach high, more hot temperature is the question. So maybe to further couple to another system to upgrade the temperature and things like this. Air, I think, is not the same objective. I think air is more adapted to building needs because it's quite flexible. And now the new building are quite well designed. So I think the heat needs are less important, and we have to find also. I like a lot to play with air because yes, it's flexible to inject or to get rid of or to mechanical or to have natural ventilation. Maybe in the water, PVT water, it could be also a direction to find thermosiphon system that could sometimes be use a pump, sometimes use natural circulation. To have flexible PVT water could be interesting, maybe also.
Yes, sir.
And the coupling with heat pump, yes. With PVT with heat pump is a good coupling, yes. There was good experience on that.
And there was a discussion about this insects and then maybe butterflies. So that how we are mimicking their things like the spores and there, and it's very difficult to understand their behavior practically, and then understanding their behavior and implementing in the real.
No, yes, in
It's-
reality
it's-
you are right. We couldn't reach. We could never. I think we will never be able to reach a real insect or plant interface because it's too complex. All the functions are integrating in the same materials. Whereas for us, usually when we want to add some function, we add materials. To have one materials that have all the functionalities is very hard. But at least you can identify one property that seems to be interesting to develop and to enhance. Usually it's that in the whole complexity of only single materials, there is one property that could be interesting to use for our purpose. And it is what we call bio-inspiration. Then it's better, I prefer bio-inspired. We get inspiration of what we identify. That biomimic is strong. And I think we never biomimic an interface. The domain where it's more simple, it is the domain of some materials and more active, where for example, they are using some physical, geometrical, they are reproducing geometrical interface. For example, for swimming pool, there was a Speedo that has developed a swimming coat that has the same geometrical structure of the skin of a shark. And it was very efficient because when you look at the skin of the shark, there is small geometrical design that allow to generate cavitation, water cavitation. So that means that water cavitation, it is evaporation of the water become gas. That means that the shark, when he is swimming very fast, is swimming on the vapor, not on the water, because all around the skin Finally, there is cavitation, so there is a small layer of vapor and not of water. So it's going very fast. It has been also implemented in the army for the missile, submarine missile. The what do we call that? Torpille. That's the same process that they generate cavitation, and so they are traveling very fast. So geometry is more easy to implement, but yes. And what is difficult is also that in one material you have multifunction, but all the scale have a specific design. When you look at the nanoscale, there is a specific design that will imply a property at a microscale, and the microscale design have a property that will imply a macroscopic, so very energy consuming if you want to reproduce that. But modestly, we can at least identify one interesting property and try to, with other materials, or to generate the same property or generate the same phenomena. It's at least one innovation.
Yeah.
Yes.
Any question?
Okay, thank you, sir. Actually, I do have two questions. One is regarding that PV system with painted inks.
Which one?
PV system.
Yes.
That was painted with inks.
Ah, yes. It is. It is also here. You see, we have made wood, terracotta, and stone.
Yeah, my question here is, so far, we do have efficiency decrement because of dust.
Ah, yeah.
So
Yes.
when we are painting inks on PV system,
Yes.
its efficiency will decrease.
Yes.
Or else, actually now, what I'm observing is the paint is overall.
No, it's just some point. Like you see here, there is a zoom. Yeah. It's not fully painted.
Alright,
It's just
okay.
a printer that puts some dot.
All right.
And
Okay.
so when you are far, it looks like uniform, but when you are close, we were playing with the distance between the dot to find a good compromise between loss of efficiency and far aesthetical aspect.
Okay. The other question is regarding building integrated PV system.
Yes.
How can we perform its maintenance, and how can you identify the faulty module or PV panel? Because different, maybe so many panels are there that are integrated with building. Maybe the building, maybe it's too big. So I do have doubt on its maintenance.
Yes, you're right.
stuff.
It's a good question. It's less easy to have access to the PV integrated than on a PV central. You're right. For roof or for facade, you are not going on your roof every day and look at the facade every day also. So we are working on the identification of problem, if there is. And so this Friday that we will speak about performance again, a tutorial. I will present you tools that we have developed with a startup. We create a startup that is able analyzing the signal of the facade or of the roof to identify if there is a good operating condition or if there is a problem. So the first point is to be able to identify that as soon as possible, because we identify that some collectivities, for example, wanted to show the example and integrate PV system, but they didn't create a service in the collectivity to look at the PV panels. So finally, they put the PV panels and nobody follow if it is operating well. They don't, and so it is important to have such kind of alert to see there is a problem, or you should clean your PV, or because the first point. And after, yes, it is the access for the facade. You're right. It is more costly to go and change PV panels in a facade than in a PV central. So the first point is to be able to identify as soon as possible when there is a problem or decrease of the production. And it's not so, there is not so many tools that allow that. When you will put a facade or a roof, you will not put a meteorological central, put some thermocouples to follow the temperature. So it's not possible. So the tools that we are developing are analyzing the production, and depending on the production, I show you some, for example, when there is shadow, there was a drop like this. So is to make the link between phenomena and the impact on the PV central. So, and to identify, so if there is that, it is because there is a dust on the one panel. If there is that, it's because one panel is destroyed. If there is that kind of production, it's between, so it's the first part, which is also part of research at that time, to be able just only on few signals to identify the problem, but also the origin of the problem. Because to identify that it is producing less, it's easy, but never done. It's never done, but it's easy to see that, no, today I should have produced more. Because there is a direct link with the meteo. So one day to another is different meteo. So you don't know if it's a good production or not. Okay? But it is a more simplest thing. But then after is to, if it is not the result, the production which is expected, is what is the origin of this discrepancy. So it's also a large field of investigation.
So online participants, if you have any questions, you can raise your question.
No question? Okay.
So we'll break for tea.
Okay.
And, maybe after 10, 15 minutes is fine. 15 minutes. After
Okay.
15 minutes.
Can you hear me? Just have a look. So sorry, I didn't notice that there was a small earth crust. So that's why I didn't understand. Was everybody was like this? I was in my mood and. And okay, so as a tutorial, it is concerning solar pumping. But if you have followed my previous speech, I said that solar pumping is the more simplest solar installation. So I will present the solar pumping, how it's designed, but there's no more difficulty. There's no difficulty on such a thing because there's only solar panel, pump, and that's all. So in terms of tutorial, I will present you an application, okay, what is the principle, but I will prefer after that you work on a more difficult design. So it is solar plus battery, okay? That is the reason why we print and you... did you send the mail to everybody? Okay, so and it is more difficult because you have to design the solar PV and then also to design the battery, to choose the battery and to see how to connect them, okay? So if you agree, I will speak about that. And if we didn't have time to finish the tutorial that I proposed to you, we will start tomorrow morning to finalize it, okay? Like this, tonight you can have also time to look at my lecture, how to design, and to come back tomorrow to finalize this. Okay, so solar pumping, it's very simple, but could be very essential in some place where there is no grid and where there is need to manage the water. Here, sorry, it's in French, but I can translate. First, for solar pumping is to identify what are the needs, okay? It could be used for fire, when there is fire, it could be, but it could also be for the given some resource, water resource for village, for human, for animals, for agriculture. So this is in French, but you will fully understand. So for human, in order to survive, it is a need of 5 liters per day, okay? For the conventional living condition in Africa, it is 30 liters per day, sorry. For animals, of course, you have to identify also what are the needs. For the cow, it's 40 liters per day. For goat and lamb, 5 liters. Horse, donkey, camel, and agriculture also. So finally, the principle of design is all the time the same, to be able to identify the need and then to answer to the need thanks to solar energy. So sugar cane, wheat, rice, so you need for agriculture a large amount of water. So this can help you to design. You need to identify what is required in terms of quantity. So the principle is quite simple. You are pumping in a river or in a hole in order to store the water in a tank. Okay. And so the main issue of the PV will be to bring electricity to a pump, okay? And so the whole problem is to clearly identify the amount of water per day that you have to pump and to store. So the distance where you have to bring this water, there is two things which is important. It is the flow rate, okay, for a day. You know that, for example, during 5 hours you will be able to pump during the day. So it gives you the flow rate in order to fill the tank, okay. And the other thing which is important, it is what is the distance, what are the tubes to bring the water from one point to another. And what has to be done is to evaluate clearly the pressure loss along the path of the water. Okay, so there is two things. First, you identify the quantity of water per day. Then, depending on the location, you look at the climate. Is it a very sunny local area? If it is very sunny, you can say, okay, I will pump during 5 hours. So it gives you an idea of the flow rate to fill your tank. Then, regarding the distance between your storage to the way to pump, you have to evaluate the pressure loss. And so with these two parameters, there's two main parameters: flow rate and the other parameters for pumps, you know, it is manometric eight. Manometric 8. So the manometric 8 is considering the difference of altitude plus the pressure loss. Okay, if you forget that, you will never reach the top of the tank. Only if you just consider the difference of altitude, you will never reach, because pressure loss, well, it is here at the aspiration. It is all along the circulation. It is, we call that linear pressure loss because there's friction. But the more important is singular pressure loss. When you have a change of direction, you are losing energy finally, and so it's essential to consider all. So these two parameters are essential for the choice of the pump. Okay. And there is many different pumps. So I repeat, first to identify the tank, then identify the volume, the time of sun, time for pumping, it gives you the flow rate. You have to also evaluate the pass and so. Okay, there is many different ways to identify the pressure loss and the manometric height. So manometric height, as I told, it is HM here. It is difference of altitude plus pressure loss. Pressure loss is not expressed in this, it is written here in meter equivalent of water column of MCE. MCE column of water. I don't know if you have made the hydraulics. You have made hydraulics? Okay. So you can formulate the whole energy in terms of altitude. So this potential energy. Okay. So in one point you have this potential between 2 points. If you are losing, it is delta H, and this is proportional to meter. If it is water, we say that it is equivalent water column. So it's not the objective of the topic, but so it's to identify the difference of altitude is quite easy, but this has to be accurately done, but we will not spend some time on this. It is more hydraulic. Okay, but there is several. So for linear, so the friction with tube, the pressure loss is related to the length, of course. The more the distance of the tube is important, the more the loss is important. The diameter of the tube, and so the velocity power 2 divided by 2g. Okay, lambda is the linear coefficient of pressure loss. So it's related to the rugosity, the roughness of the tube. If it is plastic or if it is copper, it's different. Okay, if it is concrete, it could be concrete for big tube. The loss is bigger than plastic, for example. So this is the meaning of the flow characteristic. Is it laminar, turbulent, and of the roughness of the tube, viscosity of the liquid, but for us it is water. So the main principle, yes, it is to be able to evaluate that along the path. So for this tube, for this tube, for this tube, for this tube. Okay.
This one is a submersible pump, right?
Yes, this is a. I will show you different. So usually you have this or you have this, and it is two different kind of pump. Just to show you, but yes, it is a submerged pump. Yeah. Okay. Okay. So first is linear, and second it is singularity. So this is also something that could be formulated like this. And this you have a singularity coef. So if you have a change of direction, if you have a van to open or to close, each different components on the path is a singularity. And so you can find easily, and when you choose an hydraulic component, the coefficient of loss, okay, which has to be applied like this. Okay, so this linear, this singular allow you to identify that. It is essential to identify that, to combine to the different of altitude in order to have the good manometric height. Okay. So the meter of column of water. Is it clear? Do you have any question regarding that? So through this H of the pump, it is easy to come back to the power, hydraulic power. Sorry, it's equal, it's not different. So to become what I have meter here, it is easy to find what we have to do. It's to multiply by the mass. So the mass is the density of water multiply the volume flow. Okay, so this is mass flow rate. Okay, and gravity acceleration is missing. mgh. mgh, it's proportional to an energy, but as it is a flow, it's m divided by time, it's become power. Okay, so this is the hydropower that we have to provide to the water to take it from the hole or from the river to the tank. Of course, there is an efficiency between the engine of the pump, which is electrical, to the real power transmitted to the water. Okay, so for the pump, the electrical power is PE. So it's bigger than the hydraulic power. And you have here an efficiency of the pump. Okay, so it could be 80% of efficiency. There is several things that make a loss. It is a mechanical piece inside. There is some friction, so there is some loss, okay, by the work, and also efficiency of the engine by itself. Electrical engine is also eating a bit by Joule effect, so you are losing. So globally, this global efficiency take in consideration that compared to the electrical power of the pump, you have loss to provide to the water. Okay. So as soon as you have the electrical power, it's finished. You know the electrical power that you have to provide to your pump. Okay. It's clear? Some question? So you have different kind of pump. You can have some pump that are submerged. You have floating pump also if it is on a river. So typically it will be this kind of centrifuge pump that you will use if you are in this configuration. There are 4 types of pump for this kind of configuration. If you are submersible, it will be that kind of pump, centrifugal submersible pump, because you have many different pumps. You can find that, which is, I don't know if there is some in India, or you can, there is also in France some. It's also convenient when it is a windy area. You should take that better than solar. It's the same. And so it's yes, piston pump. So interesting. The previous also ancient was also the same. Okay, and so here you have the 4 different kind of pumps that could be used. And depending on the volume that you want to, the main 2 parameters is the flow rate, the volume you want to bring, and where you want to bring. So the 2 parameters is manometric and flow. Okay. Some pumps are very good for big flow, but small manometric properties. For example, when there is flooding, okay, here there is a flooding in the building, you will put a pump directly here that a very small manometric height, but a very good capacity in flow, okay. The reverse, you can have weak flow, but big manometric height if you are going very deeply, but you can't have both. It's very rare. Then if you want to have both, you have to combine different pumps. Put some pump in series or in parallel. Okay. If you are in series, it's to have what? Big manometric height or big volume? In series, so it's to have a big manometric height. You can put several pumps like this. In parallel, is to have a big flow rate with the same manometric height. So you can combine, okay? So this is the choice of a pump is like this. What flow and what manometric is the main 2 parameters to choose your pump. Also considering the way they are operating, the environment, if they are floating or if they are submerged, of course. This is not made to be submerged, for example. Okay? So this is characteristic. It's in French, but you can recognize the flow rate in liter per hour and the manometric, and you can see if it is centrifuge pump or volumetric pump, how they behave but so you can find that everywhere. So I was identifying that. We have compute that, the hydraulic pump power, okay, and determine, thanks to the efficiency, the electrical power. So I've made a direct link between electrical power and the global efficiency of the pump with hydraulic power, as you remind. Okay. So quite simple to identify the electrical power that we need here. So for an example, the energy that is required per day, so it's approximation considering the G, the volumic mass, so this coefficient is coming from this. We can express the required energy per day, but you are able to identify by yourself exactly, not taking in consideration this. This is to considering that there is a full day of pumping, 6 hours or 7 hours. You take that in consideration to find that. The pump efficiency, depending of the pump, they are not so good. For example, the mechanical one that we see that with the wind turbine is not so good. But the interest is that there is no consumption, no electrical consumption. But you can reach 80%. So we can then throw this energy that is required per day to identify the peak power of our PV central. So it is energy required divided by the global irradiation of the place, okay, in kilowatt hour per square meter and per day. G is a jour. Okay. Then we deduce and also considering that there is a pump efficiency. Then you deduce the flow. You have the flow of the pump, and that's all. So when you have the peak power, then you can select a PV panel you want, and the way to use it. Is it clear? Of course, you have to design your grid and the size of the tube for the flow that you want. We avoid to have too much pressure loss, of course. We select the radiation for the bad day. It could be constant along the year, but if there is some months where there is a low level of irradiation, you choose that for designing your pump or your system, because it's important to have water which is necessary all along the year. So as an application, Ouagadougou is in Africa. The estimation, so when you look at is it for agriculture and so on, is 20 cubic meter per day. The difference of altitude, so probably it is in a hole, okay, in a, I don't know, remember, so it's not in a floating pump, it is underground. So 30 meters. There is 100 meters of tube. Global horizontal is around 5.2 kilowatt hour per square meter per day in December. It is the worst month. The efficiency of the pump is not so good. For these pumps that are emerged is 30%. The energy required per day is 1,635 kilowatt hour per day. Then you deduce the peak power, considering the efficiency of the pump. You will have to install a bit more than 1 kilowatt peak. So for the unit, it's French unit. This in French means crête, but it is the same as peak. So you can find both kilowatt C or kilowatt P. And the flow of the pump is 4 cubic meter per hour. So that means that it will operate 5 hours. Because we want, consider 5 hours of run, of operating. There was only 1 meter of loss. Okay, so it's not bad due to the different. So when we have the peak power, then we have to look at different PV panels that we find on the market. Okay, so if, for example, we find Siemens PV or Voltec Solar PV of 1 square meter at around 200 watt. Okay, you will put 5 panels to reach your peak power. Okay, it's better to oversize than to be a bit down. So the photovoltaic installation that is identified is for 1 kilowatt peak. The cost is quite. I think now the cost of this should be more around 2,000. This price is a bit higher. The maintenance, so it's important also to the cost to take in consideration maintenance. Okay, maintenance here quite simple. It is related to the pump or to the PV panels. Okay, there is no battery, there is no electronic device. So we said that it was an estimation of the maintenance cost, and running 20 years, we didn't have this aspect about this coefficient. If I have time before the end of the week, I will show you the formula about that. But so it's an estimation of the cost per cubic meter to evaluate the price of the pumping watt cubic meter finally to give a price if you after sell it at the scale of a village, for example, or it's just okay. So now it's finished. If you have 1 kilowatt, you choose a panel on the market, and in order to be around 1 kilowatt, better to be a bit higher. Five panels would be okay, or 4 panels. So some examples you can find. We have seen that also here. Some PV like this with a tank, more simplest one, a bigger one, and for agriculture. Do you have any question? So it is the simplest solar design in terms of PV, because there is nothing else than PV panels. It's more difficult when you have other components to deal with. That's why we didn't spend too much time on this. You see just the principle to identify the need, then to make the link with energy, and then directly size the PV panels. Okay. I would like to spend more time on the tutorial I proposed to you. It's autonomous also, but including battery. Okay. So this is that. So, sorry, it's in French here. No, I made a mistake about the question. Okay. So it is a real also installation. This installation is combining wind turbine and solar PV. It is for a school in Burkina Faso. The principle is that, so it is a hybrid system, as we have seen, okay, and to have battery, then to use it. So the school is here. We will not consider that. Just focus on the PV, okay? So what I know, it is the place where it is. Okay, so I have the latitude, the longitude, 2 fundamental parameters, especially latitude, okay? I know also what is in this school. Okay, so in this school, I have lighting, okay, light bulb inside the building. I have light bulb outside the building, so it is for the night to have light outside. There is inside ceiling fan, so air for comfort, refrigerator, and there is an office with a computer, radio, and photocopy machine. Okay. I know the power of each element. I know the number of each element. Okay. So the question that I will change that. I wrote in English, but so it should be in another way. What I have, but you can investigate in your side if you want to change. You can have a look, depending of the latitude, longitude, the place. You can see if you find other data regarding the radiation. Okay, but we have that has been established on a statistical approach of 22 years. So the monthly average insolation. So in January, February, So we see that the worst month is August here. Or we can have also idea of wind, but we will not consider wind. Okay. What else we have as data? We have some shortcut regarding the best inclination of the panels. It is the very simplest thing. If we want to design first roughly, it gives you an idea regarding the latitude for the best inclination we usually consider in order to produce the maximum of energy. Here, at the opposite of what I presented before, when I was speaking about facade and saying that we don't look at the maximum of production of energy because we want to be more close from the need, it is for connected to the grid. Okay? If we are connected to the grid, we can have another problem, another issue than producing the maximum. But for this kind of installation, it is autonomous installation. There is no discussion. The main issue is to produce the maximum. Okay? In my previous talk in the cities and so on, it is because I'm connected to the grid. So I want to produce not each time the maximum, but more close to the need. For this autonomous, of course, it is to produce the maximum. So these inclinations are giving, depending on the latitude, to produce the maximum, okay? The best inclination. And we have also some data regarding the battery that are available locally. But you can choose other battery if you find other battery, okay? But it's good to know also locally what are available technology. So there is lead battery and gel battery that are available. So this is data that you have. And sorry for this, it's in French. The question is, of course, design the PV central. Design the storage, donc the battery. Select the material, so which PV panel we'll see for estimation of economic estimation, but and how they are connected. Okay, that means how many in series, how many in parallel. Okay, so first will be to identify the need, energy need, okay? Then what is the second thing to identify? Autonomy, okay? We want 1 week, we want 1 day. It's a huge impact for the battery, okay? And then design the PV, identify the model of PV, how you will connect them. Whatever the connection, you will have the same power. Okay, so the problem is not to reach the electrical power you need, is how to connect them to have the same voltage with the battery also. Okay, so you have to have a connection of PV, parallel series, then it will guide the inverter, and then it will also guide the way you will connect the battery. For sure, for such installation, they will have not one battery. They will have several batteries connected also. Okay? Is it clear as an objective? We didn't investigate the way to combine the battery. Alors, one battery. There is two characteristics for the battery. There is the voltage, okay? So could be 12 volt, for example. Okay. And the other characteristic of a battery, we have more investigated this characteristic, is the capacity. Okay. The capacity, which is in ampere hour. So it could be, for example, 100. Okay. So if I'm doing that, what kind of connection is it? Series, okay? So what is the consequence as a voltage and capacity? It will be equivalent to a big battery, okay? And so what are the properties of this battery? Because when you are in series, the voltage are addition, okay? So it will be equivalent of battery of 24 with the same capacity. Okay, and so as a reverse, when you put some battery in parallel, okay, en parallèle, you will have a battery equivalence, which is 12 and 200. So combining, it's like the PV modules. When you put the PV modules in series, the voltage are added. When it is in parallel, the voltage stays the same. Okay, but intensity is combined. So when you are in parallel, the voltage will stay the same, and in series, you are doubling the voltage and the capacity stays the same. So at the end, you will identify the number of battery to have your autonomy, but you will have to combine them, to connect them in order to be consistent with the PV field. So to go at the end of this tutorial, not to spend 1 week, we will make a gross assumption, of course, okay? But just to understand the way to design it. So for example, if I look at the battery, nominal voltage is 2 volts or 6 volts. So maybe, as I told you, PV modules is around 12 or 24 volts. For sure, we will not choose such a battery here. It's too small. We will have too much battery. So, depending, gel battery could be interesting and maybe more expensive, but you can choose. Or lead battery, probably at 6 volts, could be interesting and less expensive. But probably it's one of these to have a better connection, and it will depend of the voltage that we will have when we will plug our PV. But you see, if you want to have 24 volts or 48 volts, you will have to put the battery in series, and then depending of the intensity you want, add some rack in parallel. Okay. Don't know what time we have. 30? 30 minutes. Okay. So we can start. I can leave you think about that, and then I will. So first is to identify the energy need. Okay. So there is not too much. There is not too much device. So we have to decide. An important point is not sufficient like this. What information is missing? Time. Okay. So we have to make an assumption about time. So for sure the light during the night will not operate during the day. So it could be maybe 5 hours during the night. For the day, at what time the school is opening, at what time it's closing. Refrigerator, it could be continuous, 24 hours. Computer, so I have made the assumption that the lighting inside the building is 5 hours. During the night, it's 12 hours. For the comfort inside the building, it's 12 hours. Refrigerator, it's 8 hours, so that means that it will not operate constantly, but just when the people are coming at the school for them to put their dinner, for example, for lunchtime. Computer, radio set, photocopy machine, and maintenance could, if you want to put an electrical engine to make some thing, you need to think about that. So it's assumption, but it's up to you, if you are a designer, to discuss with your customer to see when the school will be open. What do you think? You think the refrigerator will operate all the day or just for your lunch, to the morning to keep your meal safe? The fan, and so this has to be established with discussion with the client, okay? So we can go on this assumption to have the same data, if you agree. Another thing that is different regarding the lecture I give it to you, usually I stop at this to consider that this is the energy that I have to provide and design it. As it is a school or something that could evolve, the number of children can increase. So in this case, it's not so stupid to measure this energy in terms of planning the future evolution of the school, because it's stupid if you just design for the needs today that you have to change your PV central or the connection because you don't plan that maybe the number of children will increase. It's not technically, it's not a problem to add some PV panels. What is the problem if you have your PV central that operates since 10 years, okay, and you want to add new panels, for sure they will be different. You have 80% of chance to don't find the panels that you bought 10 years ago on the market. It will be disappeared because there are still improvement on new PV panels. So if you find the Voltec Solar 140 on the market and 10 years later, for sure you will not find this. You will find Voltec Solar 150 or 100 more efficient for the same surface. So you can, it's a problem after when you will plug to your existing PV central, because automatically you will generate a mismatch. They will have good panels that will operate very well and old panels that were aging together and working in the same configuration. So it's not so easy after to don't make disturbance on existing PV central if you are changing some panels. Because if you are changing, you are adding some more recent panels that are more efficient, so that will not operate like the neighbor. And I told you, if the neighbors are not operating the same way, it creates mismatch, and so it's not good for the whole PV central. Okay, so at the beginning you have at least also to think about future evolution, than to say, okay, if it's not enough, I will add some panels in 5 years, because it's simple. Yes, you can add some panels, but sometimes it's better to change every panels, so it has a cost to operate in the same configuration than to add new one. Okay, it's the same if, for example, you have a PV central and one PV panel which is broken. If you change this one, it will operate differently because it's new, the efficiency is better, so it's induce mismatch. Okay. So it is also one advantage to add PV with micro inverter. You can avoid this problem of mismatch if you have all an installation with a micro inverter. So if you add a new one with a micro inverter, it will not disturb the other. Okay. So here I suggest to measure. So 30% is not negligible, but it's to be able to evolving in terms of needs inside the. But this could be also discussed with the customer. Did your school in this area expect to grow in time? So do you have any idea of the number of children that will increase, and so on, to try to give you an evaluation for the sizing of your PV, okay? The more difficult thing is to identify reasonably the needs. Okay. Here, so there is also two possibilities. I I told you that we can also focus on the bad months, but here for the bad months it is holidays, the school is not working, so it is by discussion so that you know that. So it's a bit stupid to focus on this if the school is closed, okay? But otherwise, if it's operate all the time, you will choose that. So here what I said is that I choose a mean radiation if I have a look here, which is not far from this value, which is 5 kilowatt hour per square meter or per day. But you can choose 4.84 if you want, okay? To be sure that focusing on that, you will oversize the PV installation, but here I have already oversized it, so it is assumption. All is in question is a question of the assumption you want to take. There is no bad assumption or good assumption. You are obliged to make some choice, okay? So here, if you want, you can focus with your data on this, okay? The bad months for the value. Okay, so I leave you to think about now a bit more. We have the energy, we have daily load, so we have the chosen what is the mean radiation factor that we will take. Do you have question? Okay, you have it. Okay. Oh, so in principle, you should be able to give me an evaluation of the power. So I have to choose a panel, okay? Now, what kind of panel? So what I suggest you is to take the same panel, so module, sorry, with a power. So it is Siemens solar module SP 104/12. The power is P. Sorry. We can guess it is 140 watt peak. We can guess also the voltage. The reference is 104/12. The voltage is given by the voltage is 12 volt. And useful voltage is 12 volt. Okay. But in reality, you can investigate different PV manufacturer to see the price or the power. So, but I suggest you to take this. So with a power peak of 140 and a voltage of 12. But you can find with the same surface, maybe 160. For sure it will be more expensive. And a voltage of 24. You can find also different voltage, 12 or 24. Usually it's 12 or 24. So now, thanks to this model, what are we able to identify, to estimate? Sorry? Yes, but so thanks to that, what are you able to determine? Thanks to this characteristic. You're able to evaluate the energy that one panel can produce for one day. Okay? Thanks to that and that, you can have an estimation of the production of one panel. And when you have this estimation of production of one panel, compare to the global energy you need, it will help you to identify the number of panels. Okay? So I leave you, try to give me a number of panels. We can say one. It's a good. Yes, we will say for one. Somebody suggest a number? 70? More, I think. I found more, but maybe I made a mistake. We will check. Okay, so I estimate so that energy that could provide per day is 700 watt hour. The price that I found is for one panel is 129 euro. And so the number of PV panels is the global energy need divided by what one can produce. And you find 70? Me, but maybe I made a mistake. So check. So it is a global energy divided by 700. And check if you find the same. Maybe I've made a mistake because I done it.
Whenever we multiply, if we multiply 140 watt into that 5 kilowatt hour per meter square day, that multiplication gives watt square. So maybe there is a mistake.
Ah. Where?
At first startings.
Where?
140 into 5 into that area.
Yes.
First earlier slide.
So 140 multiplied by 5 kilo.
Kilowatt hour per meter square per day.
Yes. You don't find 700?
That numerical value we got 700, but the SI unit it is watt square.
Ah.
So I think
So
problem. Maybe division is there.
can you show me what?
This power is generated by one
Yes.
PV panel, and this is the what we got the
Yes.
kilowatt hour per meter square per day.
Ah, it is when you multiply.
Multiply then watt
Ah,
square.
oh, yes.
Then maybe it is
But you have to multiply that by.
and area is 1 meter, no? So
Yes.
maybe this
I've got to check.
division.
5.
Otherwise this unit we need to check.
Yes. I've got to check. Yes. I will check for tomorrow. So, so compute, and we will. I will check for tomorrow. The other question I would like you look for tomorrow, so that we have the same energy produced for sure. I've got to check that. And the second, the next step will be to determine the number of modules in series and the number of string parallel. So maybe don't determine that for tomorrow, but think about how it could be determined, okay? and me, I will check that value. But so identify the energy produced by one modules and yes, and then think about how we will compute the number of modules in series, in one series, and then the number of string that you will put in parallel. The constraint is to be balanced. You can't imagine to put 3 modules in one string and 4 in the another. Parallel will have 3 modules, not 2 here, 3 here. It has to be symmetrical and balanced. I give you also new data because depending on the power of the PV central, there is some advice regarding the voltage to have at the inlet outlet of your PV central. So for us, it will be so I found 84, but it will be a small PV central, which is between 2 kilowatt to 10. So we can select to have 48 volts at the born of the central. Yes, but usually it's yes, you're right. I think it's a shortcut. I've got to check this result. Yes. I've got to check my value. Okay, so for tomorrow, check this value. Think about how to determine the number of modules in parallel and the number of modules in one string, and so in series, and the number of string in parallel. And I will check my numbers. Okay. Do you have any question? So if you are not, we can stop here for today, and we will restart by this tomorrow. Okay. Thank you. And yes, think about that. So we'll assume that we will have 48 volts at the central born. Thank you. Ah, yes, you're right. So I made
some maybe typo error or something.
Oh no, it's 70, so this is 70?
Yeah, 70.
Okay.
Because 84 is different.
I was too tired, I think. Okay. I will check when we will start tomorrow with the same value. So the right answer, if my value are right, so 700, I've got to check. It's not 84, it is 70. If you do this operation, 48,620 divided by 700 is 70. as your colleague has checked. So I've got to check everything for tomorrow. I was too fast in my short design.
Software used for this modeling.
We were using in the past we were using COMSOL.
COMSOL multiphysics.
Yes, multiphysics.
It is possible with that.
Yes, yes.
Okay, I also an expert in COMSOL.
Yes, it's nice tool. Yes, we are using it very often at this scale. Yes. I don't know if I should keep or not. Discard. There's one key. It is your key, maybe, which is here. Ah, okay. Yes.
Dudul Das. He is a Marie Curie research postdoctoral research fellow at James Watt School of Engineering at University of Glasgow in United Kingdom. He has completed his PhD from IIT Guwahati on the topic development of an efficient photovoltaic thermal collector. His research interests include photovoltaic thermal solar collectors, form stable phase change material for thermal energy storage, heat transfer and thermodynamics, solar distillation and solar drying. He has he has almost 7 peer-reviewed journal publication, and including different almost 3 or 4 conference articles, and he achieved the best thesis award in 2020 from the School of Energy Science and Engineering in IIT Guwahati, and he serves as a reviewer of several international journals also. He was a teaching assistant for several courses in IIT Guwahati, including solar energy conversion technology, renewable energy systems, and fundamentals of energy engineering. His research area mainly includes thermal energy storage systems from different perspectives by means of theoretical, numerical, and experimental techniques. So, with this, I welcome Dr. Dudul Das to deliver his talk.
Thank you, everyone. Thank you, sir, for inviting me. So I'll not take too much time to introduce myself because Urvashi did a very good job. I think I don't know where she gets such a long introduction. So my lecture will be mainly on photovoltaic collector. So I'll be talking more about my research. Also, I'll give a brief overview about the PVT collector research going around the world. Also, we'll try to solve a few numericals, which will be very easy, I guess. So title of the presentation is PVT collector, experimental exploration and efficiency enhancement techniques. So here we'll go through some of the basics about PVT, some of the experimental testing facilities, how they operate, and then we'll go through some of the techniques through which we can like enhance the efficiency of the PVTs. It's not working. On it. Okay. Okay. Let's see this picture, this slide. So, what do you think? Like, under which scenario the modules will work better? The one at the top is like somewhere in a desert area where radiations are very high, and one in a area, let's say Kashmir like climate, where it's snowy and it's very cold and cool climate. So can you tell me like which will be the best location for installation of PV modules? From general perspective, like let's assume that both the locations are at like similar latitudes, receiving same amount of radiation, but their temperatures are different. Let's say in the again, so it's not working. I don't know. Okay. So anyone? Okay, one vote for the cold climate. Any other votes? Winter? Any more? We are getting more support for the cold climate. Anyone who is supporting the desert one? Anyone from Rajasthan? If someone from, no. Okay, so why cold? Why not this one? Like because both are same. Like radiation wise, both are same. Yeah, it's the game of temperature, and we will explore about this in the next slides. Why the temperature plays a key role in the working of the PV modules, and that's why the concept of PVT comes into existence. Okay, let's look at this very popular figure. I think you have come across these figures in previous lectures too, because this is the basis for operation of any solar collector. If you look at the blue region, that is the region which consists of almost 42 to 45% of the solar spectrum, and that is where or that is the region in the solar spectrum responsible for operation of the PV modules. PV modules doesn't absorb the IR radiations. The red part, it has nothing to do with that. But the thermal collectors, they operate on that region from let's say 1000 to 2500 nanometer. But most of the PV cells that work within this range. But now there are like advancement in the research and material have been discovered which operates on the IR region also. Those called thermophotovoltaics, which are still at a very beginning stage. People have to work a lot on that to make them commercial. Let's say we have a PV cell, but that is put under sun. That means that PV cell will receive both UV and the IR. Is that correct? Right? So what happens when this IR radiations falls on the PV? Because it doesn't need that. Let's say we have a person who needs 2000 calories of energy per day, but we are giving him lots of food from KFC, McDonald's, and our mess food too. What will happen to him? Let's take a. What will happen to him? He will become fat, right? And if he become fat, what will happen to him? okay, obese is the other way around, like fat and obese both are like, okay, his efficiency will go down, right? Because he can't, like, then let's take a look at this picture. This is a wonderful picture I have downloaded from some source on internet. There are solar radiations falling on the PV modules installed on the rooftop of a well-designed house. Then this side, it tells us if we keep on decreasing the temperature, what will happen to the voltage output and the current. These are two main things for any electronic equipment, like, or electronic device. It's the current and voltage that determines how efficient it is. We can see that current is not fluctuating much, but there is some fluctuation which has not been like reflected from this figure. But we can see that when we decrease the temperature, operating temperature from 75 to 0, the voltage is increasing. That means when the solar cells operates at a cold climate, or let's say in a, as we already shown you in the figure, in a like snowy environment, then its voltage output increases. That means if we calculate the power output I into V, that means its power output as a whole increases. So that's the concept why we don't prefer to install PV modules on a desert, but we wish to have more solar panels or power plants coming up in the colder regions. This is what has been explained, that open circuit voltage decreases with increasing the operating temperature, whereas short circuit current density or short circuit current, we can simply tell that it increases with temperature, but that increase in the short circuit current is very nominal, very insignificant as compared to decrease in the open circuit voltage. That's why overall the efficiency degrades. Now we already get you familiar with the drawbacks of the PV under high temperature. Now let's talk about the solution. What solution we are proposing? Why not combine PV cells with some arrangement where we can extract the heat that has been generated on the surface of the PV. That means whatever IR radiation the PV cells are absorbing, we have to continuously remove it. It's more like a heat exchanger. So we need some arrangement whereby we can continuously remove the heat generated on the PV cells. So for that, we combine the PV together with a thermal collector. Thermal collector, in the simplest term, is a heat exchanger which takes out the heat from a flat surface by some heat transfer fluid. So that's why the concept of PVT came into existence. It is a system where we combine PV panel and thermal collector for co-generation of heat and electricity. That means we are getting some electrical output enhancement from the PV, as well as we can extract the waste heat that has been generated on the PV surface. And if you look at this, some of the facts and figures about the percentage decrease in the efficiency, which is very significant. Let's see, for a crystalline silicon and polycrystalline silicon, the efficiency decrease by around 0.45% per degree rise in temperature, which is little bit less in case of amorphous silicon, which is 0.25% per degree rise in temperature. So can we solve a simple problem which I will narrate? Just note down the values. Let's assume someone wants to install, don't write it, just write down the values. I wish to install a PV module on the rooftop of my home. I installed one Tata solar module which has a rated output of 100 watt. Let's say 100 watt, okay? And that has a rated efficiency of 15%. Rated efficiency of 15%. Now let's say on the summer day of, let's say 15th of July, I check the output of my PV module, but I am getting some value which you have to calculate, some value, the power output. On that day, the solar irradiance value was 1000 watt per meter square, and my module has a collector area of 1 meter square. Okay. And the operating temperature or the ambient temperature on that day was like, let's say 35 degrees centigrade. So what should be the output I am getting on that day? Rated output of 100 watt, rated efficiency of 15%, collector area is 1 meter square. Do you need any more information? Just tell me. I think you have came across the efficiency calculation in the previous lectures, because Professor Christophe and Pankaj sir already made you like to go through those equations and all. Okay, I am giving you some hint here. The first thing you have to calculate is what will be the actual output percentage conversion efficiency on that day, because I have given you the temperature of 35 degrees centigrade. It's not 25, because whatever rated specifications given for a module, that is calculated at 25 degrees centigrade. So there is a difference of 10 degrees centigrade, and I told you here that there is 0.45% decrease in the efficiency with per degree rise in temperature. Anyone found the answer? So it's very like simple, just give me a rough value. It's not that you have to calculate using the calculator. And so from 15%.
10.5.
Yeah.
So 15%, 100. So 10 is 600.
It's close to that. Okay, anyone got the answer? Just give me whatever you like have calculated. It's not that you have to arrive at the exact answer. Okay. Okay, we'll come back to this problem later on, because we have not gone through the equation yet. Okay. So when we talk about the PVTs, PVT has this many layers. The topmost layer up to number 5, from 1 to 5, these are the layers that are present in a PV, a typical PV like module. The first is the anti-reflective glass, because whatever radiations falling on the PV, you don't want that to get wasted through reflection. The second one is encapsulant, which is called EVA, ethyl vinyl acetate, which is a polymer. Then we have the PV cells, followed by another layer of EVA. That means the PV cells are encapsulated between two different layers of EVA. After which we have the Tedlar. Tedlar is a very unique material, and only one company in the world has right to produce this material, Tedlar. So they have monopoly over it. I think it's DuPont. DuPont or something, yeah, DuPont. I think DuPont produces most of the Tedlar. Then after Tedlar, we have the absorber sheet. That absorber sheet is like braced with some copper tubings. in my case we use coppers. In some cases they use materials such as, like, let's say aluminum tubes, but copper is preferred because it has high thermal conductivity. Then we have the thermal insulation layer. So this is the general construction of a PVT collector. Okay, now the first questions, because every here and now we talk about the economics, because if we already have separate collectors, let's say PV, we also have flat plate collectors or solar water heaters. Why do we need a combined system? What is the benefit of that? So to understand that, you have to carefully look at these two slides. The first one is this. It says that the PVT provides the benefit of enhanced combined efficiency per unit area. That means, let's say we have two collectors installed at your home separately. You have a PV, you have a thermal collector. That means you are getting 15% efficiency from a PV modules, which is it's a ballpark number, it's not the exact number. It can vary from manufacturer to manufacturer. And the flat plate collector, or FPC, what we call, is having a efficiency of 35%. Okay? So combined efficiency comes out to be 25%. How? Because let's say this has 1 meter square of area, this has 1 meter square of area. Let's combine these two efficiencies, 15 plus 35, it comes out to be 50 divided by 2, it will be 25, right? The combined efficiency. But let's say we have one single module which can produce both electricity and the thermal output or heat. We have only 1 meter square of area, the efficiency of the collector is same, 15 and 35, but we are getting the combined efficiency at 50% because the collector area has been reduced. The second support statement in favor of PVT is that overall cost effectiveness. As we already discussed that with rise in temperature, the efficiency goes down. And if we can keep the temperature at a optimum level, that means your electrical output will be higher. Let's say there are two houses, one has like installed with flat plate collector as well as PV modules. Here the annual yield of thermal energy, which can be seen from the bar that is, what should I say, let's assume that red, it's slight pinkish, it's 10.1 and electrical yield is 1.3 megawatt hour per annum. But when we install the PVT, you will get the same output, thermal output, but electrical yield has been improved. It is improved up to 3 megawatt hour per annum. So there is improvement in the electrical efficiency. That means overall we are having a gain. So these are two of the support statements or logic for installation of the PVTs from the perspective of economics. Let's get an overall view how worldwide, what's the status of PVT, what's the status of solar heat. If you look at the top figures, this has been taken from International Energy Agency, from their website. You can go to the link and you can see some beautiful like depictions, infographics to get more idea about thermal collection systems from solar. The top figure tells us about what are the different devices that are used to extract the heat from sunlight, which mainly combines, mainly at present almost 58% devices for extraction of solar heat is evacuated tube collector, which is like we call ETCs. I think most of you have seen the ETCs or evacuated tube collectors, which is followed by 33% flat plate collectors and then 7.4% unglazed collectors. Unglazed means which doesn't have a glass at the top of it, that is unglazed. Only 0.53% constitutes PVT. That means PVT is very like ignored, right? Only 0.53%. But that is the negative side of the discussion. Let's talk about this solar heat markets on the rise. This figure, you can see after United Kingdom and Mozambique, India is the third largest user of solar heat or solar thermal energy. It is having almost 27% of the global installed capacity. So that means the market in India is like very competitive, and we can say there is a better scope in this market. And then if we talk about this hybrid solar technology, there is almost 1.6 million meter square PVT collector has been installed in operation at present. That means almost 1.6 million collectors have been installed. These are mostly in like European region, Canada, Korea, because you need some place where you get both the heat as well as you also have the option to utilize that waste heat. Because in India, if you install a PVT collector, the heat you generally get out of the PVT is almost like 38 to 40, let's say. But we already have that temperature in our surrounding, like in Delhi during the peak summer days, the temperature goes like 40 to 45. So that is very low grade energy for us. But assume somewhere in Europe where during the winter the temperature soars down to almost 0 to 10 degree. There that 40 degrees very usable for them, for room heating, for water heating, in many applications. So that's why the European countries are preferring this technology, which has significant positive impact, and as well as they're trying to get their home installed with these technologies. So this is how we evaluate the PVT collectors, how we study the PVTs. That is how we evaluate the output of the PVTs. Let's look at the collector. You can see there are two ports over there. One is the inlet port or inlet pipe, that is TFI, and the outlet pipe, that is TFO. And that V and A, these are indications for voltage and current outputs. And these two parameters are measured through a device called IV tracer, IV analyzer. And then we take the output to some tank. From the tank we circulate back the fluid, but we have to make sure while testing that the outlet fluid has to be cooled down. In our case, because we are just draining out the outlet fluid and circulating fresh fluid to the collector every time we are doing the experiment. But if you have a setup where you don't have the provision to drain out the water, then you have to make some provision such that whatever fluid entering the collector, that should be at a constant temperature. It should not be that at some time, let's say you are doing the experiment for 1 hour from 10 to 11, at 10:05 your inlet temperature was 25 degrees centigrade, but as you carry on your experiment at 10:30 your temperature goes up to let's say 30 degree, which should not be acceptable. You have to keep the inlet temperature close to 25. So that is one of the challenges, how to design that inlet fluid conditioning system. But there are some heat exchangers coming up or cooling systems through which you can maintain that steady inlet condition. Also, if you look at these two figures, you can see on the right, that is the pyranometer. That is used for measuring the solar irradiance, which is a silicon type pyranometer. There are different types of pyranometer you have seen. There is a glass dome type, or that Kipzonen, there is a brand. They produce a dome type pyranometer, but this one is silicon type. And this is one of the setup we have developed within our lab. Like this can be operated inside the lab. You don't need the actual sun. You can create radiation that is similar to the sun. When I say similar to the sun, the radiation cannot be similar to the sun. It should be similar to the spectrum that is generated by the sunlight. So I'll discuss that. So you can see there are light source at the top. There is a platform where you can keep your PVT module. You have the similar setup, but within a room you can do the measurements. So these are the main characteristics that you should keep in your mind to develop an indoor facility, indoor collector testing facility. The first one should be the spectral match. Spectral match is a like parameter which says how close the spectrum generated by your artificial lights is similar to the actual sunlight spectrum. So that you have to measure. Second one is non-uniformity, and the third one is temporal instability. I'll discuss one by one. The spectral match, let's say, if you look at this figure on the right, towards your right, that says the blue colored graph that depicts the spectrum of the actual sunlight. And the red one is what we have got from our like setup. We combine metal halide and LED lamps to get radiation that is somewhat close to the actual sunlight. And our spectral match was around 0.68 to 1.95. It has a complicated formula equations to calculate. I'll not discuss about that. If you wish to, then you can go to the there are several websites. Whatever like companies that manufacture LED lamps or metal halide lamps, or let's say xenon lamps, they will give you those values, how to calculate the spectral match and all. Then what is non-uniformity? I'll show you this figure once, this setup. If you can see, the PVT modules has been kept somewhere which is at a distance from the light source. And these PVT modules are generally of a shape mostly rectangular, and we need the radiation to be fall on every point of the PVT module at a same like with same magnitude. We don't want, like, let's say we have divided this, yeah, I can't see, yeah, but it's not working, I don't know. Laser is working here, but it will not work, right? Okay, so what I'll say from here, let's see this gridded section. Let's assume this is our PVT. Here, if we look at, I have marked different nodes or different points. We want our solar testing facility to provide same magnitude at each and every point. There should not be a huge difference between this point and this point, or this point and this point. If that happens, what will happen? When we place the PV module, there will be like difference in the generation of current in every cells, and that will hamper the overall power output, because these cells are connected in series. These are connected in series. So if one cell like suffers from lesser current output, then the entire module will suffer the problem. So we don't want a non-uniformity in the light generation through our through our setup. So to calculate that, we have to find out two major parameters. For that, we have to calculate the the output or irradiance level at each and every point. So it's a very lengthy process. So let's say there are 2 points, let's say this point and this point. Here we got the maximum irradiance, let's say 1000 watt per meter square, but in this point we got a value of like 900 watt meter square. that means there is some variation. And if we put those values here, we'll get the non-uniformity. Let's say we we measured the irradiance at each and every point. Then out of that we found the maximum and minimum of those points. And if we compute, put those two values in that formula or that equations, we'll get the non-uniformity percentage. So that's the simplest way to calculate the non-uniformity. Now let's take a look at how we calculate the instability. It's the temporal instability. That means which time is that value at a particular point is varying. We have to look at that also. If we look at that instability, we can see the radiation is not varying much with the time, but it's varying somewhat with this with location wise it's varying, but with time it's not varying. So we can say that our setup performs well, at least acceptable one for evaluating the efficiency of the PVTs. So this is a very useful setup, because in a region like Assam, you will not get, it's very difficult to get a clear sunny day which is like necessary for evaluation of solar thermal collectors, but this setup can make you equipped with like a wonderful evaluation of the collectors within a lab. You don't need to go outside. Based on those parameters, we can classify our indoor testing facility based on like following different standards, international standards. What we develop falls under C category, but it still works. Now we are coming back to the maths. How we calculate the efficiency? Don't go to the figure, but because this is a very it may feel complicated, but assume that the sunlight is falling on the receiver and there are some losses which is due to, which we call optical losses, due to the glazing on the top of the collector, and that whatever heat we are getting after optical losses and other losses, we are feeding that into some thermal engine, let's say thermal engine, because whatever we are calculating, we have to calculate based on thermodynamics. Whatever efficiencies, whatever exergy efficiencies, energy efficiencies, these are nothing but basic thermodynamics. So we assume that our module is somewhat like a thermal engine, and we are getting the heat from a source which is nothing but the sun, and we are rejecting the waste heat to the ambient. For that, to calculate the exergy efficiency, we need some equations. The most simplest one is the similar to the Carnot efficiency, which is nothing but 1 minus T ambient divided by T sun, which is the simplest one, which is the first equation that was proposed in 1950s. But later on, the researchers like Patella and others, they found that this is not the appropriate equations for calculations, so they added some other parameters into it and they made the equations complicated for us. And this is the new equations for calculation of the exergy for the incoming solar radiation. Now we'll try to do a simple calculations. Just calculate the Carnot efficiency of a solar collector using the following information. That means the Carnot efficiency tells us what is the maximum output a solar collector can give. So for that, what you have to assume or you have to take, let's say the ambient temperature today is around 23. So take 298 Kelvin as the ambient value, and the source is the sun, and the sun temperature is 5770 Kelvin. So just calculate what should be the ideal Carnot efficiency for the solar collector. Or you can assume that temperature of the sun to be 6000 Kelvin, or also you can assume the ambient to be almost 300 Kelvin to make your calculations easy. So try to do this simple like okay, 0.94. Okay, so it should be around 0.94 to 95. It should range in that. That means what we showed you in the earlier slide, that a thermal collector can go up to 35%, right? Efficiency of collectors are 35%. But what Carnot says, Carnot efficiency says it can go up to 95%. Under ideal case, like you can go up to 95%. That means there is scope of improvement. So taking these mathematical equations further, these are some of the equations which we have to use for calculating the efficiencies of PV and PVT collectors. I think you have already came across these equations several times. Now let's go back to the problem I have given you a few minutes back and try to use these equations to calculate and arrive at a value. Just use the top equation, what is the electrical efficiency, but calculate how much degradation of the efficiency happens when 10 degrees centigrade of temperature is raised.
I think there was similar problem last class that professor has shared, right? So now we can distinguish like how this exergy efficiency can be defined. So it is exergy output by exergy input. So output can be found out by electrical plus thermal, and input what the expression is expressed by the speaker. So it is like 1 minus 4 by 3 TA by T sun plus 1/3 and then multiplied by TA by T sum to the power of 4. So if you substitute this, and then you can find out the exergy efficiency. Okay, and also we know how to calculate thermal efficiency and the QU, and that information also known. Okay.
So any answer? Okay, you can continue calculating that. We can move on to the next slide then. Okay, these are some of the typical values or performance of commercially available PVTs. It's a good sign that there are companies which are very popular, they are manufacturing the PVTs. So you can see this figure, the figure on the left or the graph on the left, it tells us what's the variation of the thermal output with respect to electrical output. It tells that if we have to increase the electrical output, or when we have a module that gives us a higher electrical output, we also have a higher thermal output. This is because if we have to get higher electrical output, we need a higher collector area. That means we can get higher thermal output too. This too tells what is the price of the collectors when we keep on increasing the electrical output. That means if we have to increase the electrical output, we need to compromise on the cost, because in a PVT maximum cost comes from the PV cell like costing. It's not from the thermal part, it's from the PV part. These PV cells are expensive, but now their price has gone down. It's below 40 rupees per watt. So it's a good sign that the PVs are becoming cheaper and cheaper. So we don't need to worry much about installing a PV system at our home. And as you know, like there are schemes, Prime Minister Har Ghar Bijli Yojana, or these has made the PV to be a household thing in next few years. And one of the interesting fact about PV is previously there was a misconception that PV cannot operate under like cloudy environment. but now it has been a well established fact that PV still operates under the cloudy environment, because it's the European countries which are installing most of the PVs. It's not the countries in the Middle East or not in India or not in South America. It's the European countries which are having maximum installed PV capacity. Can you tell me which is the largest solar park in the world? Anyone? Which is the largest solar PV park in the world? Solar park, that means it's a solar power plant. Let's say which is the largest solar power plant in the world. If I have to talk to you about which is the largest hydro plant in the world? Anyone? Okay. Which is the largest solar plant in the world? Okay, one. Okay, one Gujarat. Second Gujarat. One Rajasthan. Okay, Riva is in like I think MP. Okay. Tamil Nadu was okay. It's not operational yet, but its largest one is at Phadla in Rajasthan. It's I think 2200 megawatt. The second one is Kamuthi in Andhra Pradesh or Telangana. I'm not sure about that. Reva is all like, so it's a good sign that India is having the largest power plant, PV power plant in the world, and we are still going higher. That means 30 gigawatt to be installed by Adani. So that means if we have PV, there is a scope for the PVT. So that's the silver lining for PVTs. These are some of the tubing design or how the collectors, thermal part of the PVTs are designed. These are some of the popular designs. These are not some of the conventional design. This one at the leftmost have been seen by most of us. It's installed in most of the flat plate collectors too. The second one we call serpentine collector or serpentine design. That means it looks like the snake. The next one is called parallel serpentine. The few collectors joined together through a header, and outlet is also taken out by a common header. And this is the D1, we call it wave flow because it looks like a wave formed by a spider. The final one is called the spiral one. We have also studied about the spiral configuration, but our study was somewhat different because here you can see the outlet and inlet are going through the edges of the module. In our case, we provided the inlet at the center of the module. From center, we have taken the fluid and exited from the edge of the module. So these are some of the popular tubing designs for PVT collectors that are used in the PVT collectors. While designing the tubings, we have to take care of two things. The first and foremost is the pressure drop. The design should not be such that the pressure drop is higher. That means when pressure drop is higher, you need more like pumping power. That means you need high power or high capacity pumps to run the entire setup. We don't want that. Again, the second one is the cost of the tubings, because in general cases I told you copper tubes are used, which are not very cheap. So we have to take care of that. Next, I'll go through some of the slides which will like based on the research we are doing at IIT Guwahati. So we developed 4 modules. I call them M1, M2, M3, M4. The M1 is the PVT with vertical oscillating tube arrangement without absorber sheet. The M2 is the PVT with vertical oscillating tube arrangement with absorber sheet. The M3 is the rectangular spiral tube arrangement without absorber sheet. And the fourth one, M4, is the PVT with horizontal oscillating tube arrangement without absorber sheet. There is a logic behind not using the absorber sheet, because in general setup in PVTs, we have a absorber sheet which is made up of some metal, and over the metal plate we brace the tubes. But while doing that, because we are adding one like absorber sheet, there is increase in the contact resistance, thermal contact resistance, which reduces the efficiency of collection, or what should I say, the amount of temperature that goes into, or thermal energy that goes into the collector fluid. So we don't want that additional absorber sheet. We tried to simplify our design, and we established that fact through numerical studies, which I will not discuss here because that's again another area. And what we found, this M3 module with a rectangular spiral design gives us the best efficiency in terms of exergy and electrical output. We are not much concerned about the thermal output, because thermal energy has less value when it is extracted at a very low temperature. We are more concerned about the electrical output or electrical efficiency. Then we encountered one of the significant issue. Though we got some efficiency improvement, but the uniformity of the cooling at the surface of the PVT was not uniform. That means there are still some hotspot remained on the PVT collector surface. That is a serious drawback, because again, because these cells are arranged in a series connection, we don't want any cell to suffer through the hotspots or thermal hotspots, because if any single cell suffers, then entire module suffers. So we came up with a wonderful solution that we call integrating this PVT with some materials which can take out the heat from the surface and give it back to the tubes. So for that, we developed one material which can store heat. We called it PCM biocomposite, which is a combination of biochar. Biochar is a very porous material that is derived from biomass. Biomass is something that is organic, so it has some sustainability angle, and also this biochar has a good thermal conductivity when combined with paraffin wax. We'll see some slides in the next few slides about this arrangement. Okay, why form stable PCM? Why can't we directly integrate the PCM into the PVT modules? Because what is paraffin wax or PCM is nothing but the wax or candles. I think most of you have seen the candles at your home or in many other places. What happens to candle? When you heat the candle, it melts down, right? It will become liquid. That means when you are supplying heat, it melts. When you remove the source of heat, it starts to solidify. That means it takes the heat, it changes phase, and it releases heat when it changes phase from liquid to solid again. So that is the principle behind the working of the phase change material that is used for storing heat. So let's see these two figures. One, let's assume there are two glasses, one filled with the PCM, one with the form stable PCM. Form stable PCM is nothing but we combine biochar and paraffin wax. Sorry. Okay. Then we put these two things over some heat source, which is nothing but the fire. What happened to this? I don't know, something happened. What will happen? The PCM, when heated, that will come out of the glass, but this will not come out. This form stable PCM will not come out. It will remain intake. That means there is no problem of leakage, because in PVT you don't use some grams of PCM, you have to use kgs of PCM. If there is leakage, it's very difficult in the real-time applications. And also this paraffin wax or organic PCMs are non-toxic. They have a good chemical stability, high value of latent heat of fusion, as well as suitable melting point needed for thermal applications. So this is how we produce the biochar. there are two different feedstock we have used. We used softwood and wheat straw, then we pyrolyzed it, then mixed together with this biochar, what we obtain out of the pyrolysis unit, we mixed together with PCM called RT28, and then we got the composite. And this is how this A and C are the structures for the biochar. You can see there are porous structure, clear porous structures. These are in the range of nanometer. It's not something very big, it's very small. So what happens if you have some tubes which have a nanometer, which have a pores which are in the range of nanometer to micrometer, and when you put liquid inside those very small tubes of nanometer range, that fluid will not come out. Even if you reverse the orientation of this material, because due to capillarity that holds within the pores of the material, and that is what that is the advantage that we use to get our material or to develop our material. And we also studied the cyclic parameters. Cyclic parameters is that because in real time we don't want our material to fail after 10 or 15 cycles. We need it to go through a period of at least 10 years, 20 years, because the PV modules have a lifetime of 25 years. So we want some material which should at least go up to 20 years. So for that we studied our material over 1000 cycles, and we found that this material gives us the best results, or the properties, mainly the melting temperature and enthalpy, does not vary much. So this is good. Up to 225 cycles it's almost stable, but after that there is slight degradation, but still it is not much. Then this is how we applied this material into the PCM PVT, and we placed this material at the back side of the PVT module. Sorry. And then we found out some nice pictures, which is the IR images. You can see, I think these values are not very distinct. The one in the red, in the IR image, if you look at the IR image, there are two modules. One is the PV module, simple PV module, there is no modification. And the right one, which is somewhat purple and blue at the surface, that is the PVT modules with the copper tubes carrying fluids as well as the PCM biocomposite. So you can see the PV module temperature was around 43 degrees centigrade. The average temperature was 43 degrees centigrade. But with cooling, the PVT gives only 30 degree. That means there is 13 degree reduction in the temperature. So that is significant from thermodynamics point of view or thermal engineering perspective. And we get almost 18 watt improvement in the power output as compared to the PV. And we can see a 29% reduction in the surface temperature of the PVT, which results in 6.4% improvement in the electrical output. So this is what the implication of integrating the form stable PCM in the PVT systems. So this can be a very significant improvement because this has reduced the hotspots. Hotspot means the thermal uniformity has been achieved. That means all the cells are at the same temperature. They are not suffering through any thermal hotspot. That's how we can get good output, good electrical output. So this can be another area of research which people can explore, utilizing different phase change material, different tubing arrangements, and combining together to achieve more uniform cooling as well as higher thermal output. In this case, we are not concerned about the thermal output because we have done series of studies where we established the fact that thermal output is within the range of 38 to 40 degrees centigrade, thermal, whatever fluid we are getting out of the PVT, that is within the range of 38 to 40, but the electrical output was our concern, because the electrical efficiency can give you more benefit both in terms of practical applications as well as like from the economics point of view. So that was the goal of this study. So when we cool the modules, there are three benefits. One is we already discussed a lot, that is the electrical output improvement. There is increase in thermal efficiency, but with cooling the collector life also improves. It is like it has been studied and it has been like reported that if you cool the module and you are not allowing the module to go above 40 degrees centigrade, your modules can give you same electrical efficiency even after 20 years of age. Generally what happens, if the modules are not cooled or the temperature is not maintained, after 20 years of life, the PV modules start giving less electrical output. But if you cool the module and keep the working temperature below 40 degrees centigrade, then the module efficiency degradation will not happen even after 20 years. That's a like study reported by some of the researchers from IIT Delhi, as well as this research is also going on. So these are some of the designs and improvement techniques that can be incorporated in the PVTs, and these are the results from experimental studies we have carried out. So these are like we have the confidence that these methods work well. There are several other methods which you can get in the books, in the research papers, which also can be applied for improving the efficiency of the PVTs. Now we'll talk about a different area. We have talked about PVTs. Now we'll talk about how directly we can absorb the radiations into the biochar based thermal energy storage material. Do you want some break? 5 minutes? Or okay. No, it's okay. It's okay. For me, it's okay. And only 3 or 4 slides left. So, okay. So here what we did, because under normal conditions, if we don't have any devices integrated to PVTs or normal solar thermal collectors, we generally get a temperature which is like in the range of 50, below 50, not higher. So what we did, this research was carried out at University of Glasgow together with 2 other universities from UK. So we tried to come up with a device called concentrator, solar concentrator. It's a parabolic device. It's more like, let's say we cut this bottle, and we cut this bottle and we create some surfaces which are parabolic in nature. Then we call that a compound parabolic concentrator. These are the design steps. You can note this design step because these are standard procedure how you design, how you like get a collector. You can like manufacture a collector. So the first thing you need to keep in your mind is how much concentration you need. Let's say you want some applications where you want radiation of 4000 watt per meter square, but the sunlight, the maximum limit is 1300 watt per meter square, 1367 or something is the maximum limit you can go up to. Under general condition, you cannot go up to like 4000 watt per meter square. For that, you need some device which can amplify the radiations by concentrating the radiations. That means you are collecting the radiations and putting or feeding them into a very narrow region. So that is the basic principle of compound parabolic concentrator. So first thing, you need the concentration ratio. If I have to get an output of 4000 watt per meter square, let's say we simply get 1000 watt per meter square in day-to-day life from the sunlight. So you need a concentration ratio of 4. That means to get 4000 divided by 1000, that is equal to 4. So you fix the concentration ratio, and also you have to fix the half acceptance angle. For that you have graphs and charts where you can get with respect to your concentration ratio how much half angle you need. You have to fix those two things. Then after that you calculate the focal length and the height. So you calculate the focal length using this equation and height using this equation. In our case we got these two values. It's a very small setup. I'll show you the figure in the next slide. Then after calculating the focal length and height, there comes the crucial part. You have to use a software called SolidWorks to design this entire device. In SolidWorks there is a module by which you can generate such profiles, cross compound parabolic concentrator, and after that you do the rate trace analysis. Rate tracing is again another software. It's called Trace Pro. That's what that software does. Whatever design you have generated using the SolidWorks software, it evaluates that one. Let's say we assume that we will get that 4 times concentration ratio, but whatever the SolidWorks has given, that may not be the accurate one. To verify that, you have to use another software that is called Trace Pro software, which is nothing but rate tracing and efficiency evaluation. After that, once you are confident about your design, that okay, these two softwares, whatever design I am getting, whatever results I am getting out of Trace Pro software, both are matching, then you can go for 3D printing, because this kind of setup you cannot do through traditional methods, because it has a highly very complicated surface. So you don't want to damage your design, so you should prefer 3D printing over the traditional manufacturing methods. Now this is the setup. This is a very small setup. No, we use polymer. It's FDM. So once you got your concentrator, you place it over your setup, then you can use artificial light or sunlight to get the desired results or whatever experiments you want to do. So what we observed, the maximum temperature with concentration we can go up to 91 degrees centigrade. This is a very small setup and very the concentration ratio is only 4. In general, in large applications, the concentration ratio goes up to 1000. So you can imagine what will be the magnitude of the temperature. So, and also the melting of the PCM, whatever we are keeping below the concentrator, the melting time reduces from 41 to 7 minutes. So initially without concentrator, the melting time was on 41 minutes, but when we use the concentrator, it reduces to 7 minutes. So it's a significant improvement. That means in the regions where sunlight is for just 1 or 2 hours, we can utilize such devices. So that's the implication of this study. So now let's do a calculation, simple calculation using those two equations. Now I give you two values. I need a concentrator, compound parabolic concentrator. I'll give you how big it can be, how small it can be, because I have designed very small. Why I have designed this so small, this calculation will tell you. Let's say I have an absorber which has a dimension of 20 centimeter by 20 centimeter. It's a rectangular absorber which has a absorber width of 20 centimeter. Also both the dimension are 20 centimeter, so it's square. So you assume your acceptance angle to be 30 degree and I need a concentrator which has a concentration ratio of let's say 4. Now calculate the focal length and height of the concentrator that you will get. For my case, it was the absorber width was 50 mm. For that I got only, like, let's say height was 129.9 mm, almost 13 centimeter. Here I have given you the absorber width of 15 centimeter. For that, what should be the height of the concentrator? Just use these two equations. The small equations, this like for calculation of the focal length, it should be 0.5 width of the absorber into 1 plus sine theta c. After getting the focal length, you have to feed that value into the equation for the height.
What is the height?
That is the height of this concentrator.
In the equation where 50 width is applied, like 50 mm absorber width, you said 50 mm.
Yeah, W 0.5 W ABS. Width of the absorber is 50 mm.
Here it is 0.5.
0.5 is different. That's a empirical equation. So 0.5 comes from.
Half acceptance angle.
Yeah, half acceptance angles should be like, if I have considered 30. Yeah, 30. It should be 30. Just I need the height of the parabola. I don't need the design of the parabola. It's just simply the height of the parabola. This calculation will give you the view that if we just simply increase the size of the absorber, how big the parabola will be.
Melting time is, which concentration melting time?
Melting time means what is the time that we require to achieve the melting temperature
Melting temperature over.
of the PCM. We kept some PCM below the concentrator. Half meter, right?
519 millimeter.
Okay, 519. That means like half meter. Any other value? Okay, it's more or less like 520 mm or something.
519.
Yeah. So just imagine how big it will be, like just for concentrating the radiation for a 15 centimeter by 15 centimeter square. Can you view like 15 centimeter is this much, right? Do you have a scale? Anyone have a scale? It's a 15 centimeter scale, right? Just look at that scale, if I can get that. So this is 15 centimeter. Okay. So just imagine this is the 15 centimeter and then 15 centimeter. It's the small collector. To concentrate the radiation by 4 times, you need a collector or concentrator of a height of almost half a meter. Half meter, you can imagine how much? This will be 3 times, like this much. So it's very big, right? So that's the challenge. From the manufacturing point of view, it's the challenge that why we are not like going for big concentrators. So instead of increasing the size of single module, what we can do is like we can make series of modules and series of concentrator together, and that is in practice now. So we have to think of other methods to manufacture, because in a typical 3D printers, you cannot go beyond 1 feet by 1 feet of area. the area of the 3D printing base is almost like, I think 30 centimeter by 30 centimeter. So you can't go beyond that. So the cost of manufacturing goes up. So what you can do is you can manufacture smaller units and smaller collectors. So that and you can connect them in series. So that's the best solution for integration of concentrating concentrators to the like any of the solar thermal applications. Not going further, this is another setup. Here what is our intention? In typical solar like water heaters, what we have a thermal plate. From the plate the tubes collect the heat. Our intention is to remove that plate altogether. We don't want that plate. We just will use just the tubes that will be immersed within the form stable composites, and from that form stable composites we will directly extract the heat. So for that we again devised a small instrument which is again the length and width are 15 centimeter by 15 centimeter, and our next goal is to integrate one big parabolic concentrator over this collectors, because in countries like UK and like Nordic countries and other like Russia and all, or South Korea, there is one serious issue. You get good amount of solar radiation but for a very small time. Here what happened, we get the sun from let's say 6 AM to almost 5 PM during a normal day. But in UK what happened, the sun you can get hardly 2 hours or 3 hours a day during the peak summer days. Then cloud will cover the sky and then the sun will go off. So that's the issue. So what you want some arrangement through which at a very small amount of time you can store maximum amount of radiation to your storage system. For that we need the concentrator. There is no other options. Concentrator, what it can do, it can collect the radiations, reduce the melting time, because in the previous slide what I have showed, the melting time reduces from 41 minutes to 7 minutes. So 7 minutes is very small, but 41 minutes when we talk about, if I have to make a bigger system, it will go, that 41 minutes will go up to 3-4 hours. So we need some arrangement by which we can reduce the melting like time, as well as we can get higher radiation at the surface of the collector. For that such arrangement can be used. So I think I'm done with my lectures. If you need some if you have some query or you want to add something from your side, because it's not me that I know everything, because there may be some good feedback from your side, you can just, yeah, thank you. Yeah.
So compound parabolic concentrator is 4-sided, is there?
Yes, it's four.
Only just 2-side lengthy.
There is some arrangement, it's called parabolic throw.
Parabolic throw, no. Same compound parabolic concentrator, 2 parabolas.
Yeah.
2 different parabola.
But the problem is with the concentrating this compound parabolic concentrator, these surfaces are not smooth to join. Like if we have to continue on building a long system instead of like the closed one, we have to connect 2 surfaces, right? These connections is very difficult to make, because I can't show you exactly how it looks like, because these have some curvy surfaces or edges which will leave some gap in between 2 different like joints. So it is one of the challenge. So that's why it is not, you have never seen any like such arrangement where you have used parabolic surfaces for like cross compound parabolic collectors made into halves and then put into use. You always have seen this like combined or closed one.
And one more question, the M1, the 4
Yeah.
configurations,
No,
M4 was best.
just look at the exergy output. If we look at the exergy,
Exergy, okay.
yeah, just look at the exergy output and electrical output. Yeah, there is some improvement in this thermal output, but when we go to the exergy, because like our main goal was to improve the electrical output and exergy. So from the exergy point of view, M3 is best. Yeah, the reason behind that is that when we feed the water from the central, and what we have observed in previous studies, that the central part of the module is like have a high temperature as compared to the edges, because through the edges there are losses by convection, because edges are exposed to the environment, but the central part is not exposed, it's just exposed from the top. So if we feed the cold water at the central portion, it cools down and then circulates to the other part. So that's the advantage. Any more?
That PCM thickness in the compound concentrator. So for PCM you have area at the end, right?
Yes, yes.
So what could be the thickness of that?
We just, in our study, because it's a very small, it's only 25 mm. It's a very small cavity. We just tried to prove the concept. Now we are going for the bigger one. I showed you. Just look at this figure if you can. This is the first phase of the study where we use only 25 by 25 collector. Now in the next phase we are going for a 15 by 15, 15 centimeter by 15 centimeter, because we already have showed the concept that it works well. Now we are confident that this can be like scaled up. Yeah.
For the construction of this solar collector or this concentrator, we have used material like PVC, right, or polymers. But can we enhance the concentration power by changing the material like?
No, I'll tell you. The material has nothing to do with this, because the material is the base. Above this material you have to put some mirror-like surfaces for concentration. We use some thin mirrors. If you can look at this figure, you can see it from, because these are side views. If you look at from the top, there are some reflecting surfaces inside. We use PVCs, this is not PVC, or this is something, I don't know the exact name of the polymer that is used for the 3D printing, but this is very soft, it's like bendable with hand. To reduce the cost, we tried to come up with the optimized thickness of the collectors and all, because this 3D printing is not very, like, it's a costly affair.
Mirrors will be glued to the inside.
Yes, glued to the. So it's kind of a small project, but the result we are getting is very significant. So that's the thing. Now we are taking it forward and we are trying to build big setups. Okay, then thank you everyone. Thank you.
So thank you, Dhruv. It's an interesting talk. So far what we have learned about flat plate collectors in the last 2 days, about concentrators, about compound parabolic collectors, then the kind of material what you use for energy storage, which might be requiring when there is a limited exposure of sun or solar energy. So you can store the energy and use it for different applications. Okay, and while studying concentrators, the Professor Christophe has already introduced different kind of concentrators. So line focus system, point focus systems, and then 2-axis tracking, single axis tracking. Okay, and then here what you have seen is compound collectors, right? So almost all collectors are covered. And today's morning class was quite interesting, right? So we saw some of the very interesting thing. And also when Professor Christophe was introducing that building, 6th-floor building in 1960s, that furnace. It is really it is unbelievable, right? In 1960s they built that, and then they have demonstrated how this heliostat can be used for generation of a temperature close to 4,600 degrees Celsius. It's really very fascinating. And now the same system they are using for space application for material characterization. It's really interesting. And also the material so far we have discussed in this course already we have shared, and then you please go through it and also see the tutorial part. And I think he has given one problem. That problem also you try to solve. And Dr. Dudu also given one problem. And from my side, on that day we have discussed many problems actually in the talk. And of course these are very simple, but these are important problems. And since Professor Christophe has included many more things, and that's why I have not discussed. So Dudu has introduced so many things of what we have done in our labs. And in the last class, probably I will discuss about the testing methodologies of solar flat plate collectors, then solar air heaters, and then some of the interesting things about quality and what is called standards. And I'll see if Professor Christophe is not covering this power plant design, then maybe I will touch some of the things about the power plant design. So that will be concluding things for the last day. So thank you very much for your patience, and also I am looking forward very serious attendance in every sessions. So please attend. Only 2 days left. Okay. So and last day, those who are interested can write the exam, and you can earn the credit. And you should not miss the last session, the validity session, where certificate will be distributed, and then we will have a good photographs. Okay, so that will actually retain, and then this will be published everywhere. Okay. So then you know what to do on that day. Okay, so thank you very much. Okay, so.